Welcome to Natural Language Processing with Python for Machine Learning Essential Training. Have you ever wondered how your email filters out spam messages? Or maybe how autocorrect on your phone knows what you're trying to type? In this course, we'll cover some basics of natural language processing like reading in and creating structure in messy text data, and then cleaning and tokenizing that data. Then we'll cover some of the more advanced topics like lemmatizing, stemming, and vectorizing your data. In other words, converting it from text into a numeric matrix. We'll do this with a focus on preparing our data to build a machine learning classifier on top of it. We'll learn how to build two different types of machine learning models while thoroughly testing and evaluating different variations of those models. You'll have the tools to go from messy data set to concise and accurate predictions from a machine learning model to deliver solutions to complex business problems. Before we get started, I want to go over some assumptions about the background knowledge that will help you get the most out of this course, as well as some other concepts that would be helpful but not necessary. First, it'll be helpful if you have some working knowledge with Python. I won't be covering the most basic concepts, so it will be helpful for you to broadly understand how it works, its syntax, and maybe some of the basics of object-oriented programming. Beyond that, it'll be helpful if you've had some experience using the NumPy, Pandas, and scikit-learn libraries, as we'll be relying on each of those fairly heavily throughout this course. Now, for skills that would be helpful but not absolutely necessary for this course. If you have some experience with statistics, that will be helpful, but it's not absolutely necessary. In addition to that, having a basic understanding of some of the key concepts in natural language processing and machine learning will also be helpful, as we'll build off some of those basic concepts. With that said, if you don't have any experience with NLP or machine learning, don't worry. I will be covering the basics so you won't be left behind. Before diving into the course, we want to make sure that you're set up with the tools and software that you'll need to follow along. I will be working with Python 3.6. It's important to note that if you're still running Python 2.7, some of this code may not work correctly. I'll also be running code within Jupyter Notebooks. This is a fantastic tool that allows you to combine live coding, explanatory text, visualizations, and equations all in one concise package. Luckily, everything you need for this course, Python 3.6, Jupyter Notebooks, and all packages and libraries that you'll need, can be acquired very easily by installing the free Anaconda distribution. So I would strongly encourage that you go ahead and do that. Let's jump into what natural language processing actually means. There are various definitions out there, but one that I like is this. Natural language processing is a field concerned with the ability of a computer to understand, analyze, manipulate, and potentially generate human language. By human language, we're simply referring to any language used for everyday communication. This can be English, Spanish, French, anything like that. Now, it's worth noting that Python doesn't naturally know what any given word means. All it will see is a string of characters. For instance, it has no idea what natural actually means. It sees that it's 7 characters long, but the individual characters don't mean anything to Python, and certainly the collection of those characters together don't mean anything either. So we know that what an N is, what an A is, and we know that together, those 7 characters makes up the word natural, and we know what that means. So NLP is the field of getting the computer to understand what naturally actually signifies, and from there we can get into the manipulation or potentially even generation of that human language. You probably experience natural language processing on a daily basis, though you may not really even know it. So here are a few examples that you may see on a day-to-day basis. The first would be a spam filter. So this is just where your email server is determining whether an incoming email is spam or not based on the content of the body, the subject, maybe the email domain. The second is autocomplete, where Google is basically predicting what you're interested in searching for based on what you've already entered and what others commonly search for with those same phrases. So if I search for natural language processing, it knows that many other people are interested in learning NLP with Python, or learning it through a course, or looking for jobs related to natural language processing, so it can autocomplete your search for you. The last is autocorrect, where say iPhone is trying to help you to correct a misspelling. I liked this example because it shows how autocorrect has actually evolved over time and continues to evolve and learn. So with iOS 6, if you're trying to say, I'll be ill tomorrow, it wouldn't necessarily correct I'll be I'll tomorrow until iOS 7, where it actually corrects, it auto-completes tomorrow and corrects I'll into ill. So it will correctly send as I'll be ill tomorrow. So this just kind of shows how NLP is still evolving and how even super powerful systems like iOS is still kind of learning what natural language even means. Now, NLP is a very broad umbrella that encompasses a number of topics. A few of those might be sentiment analysis, topic modeling, text classification, and sentence segmentation or part of speech tagging. The core component of natural language processing is extracting all the information from a block of text that is relevant to a computer understanding the language. This is task-specific as well. Different information is relevant for a sentiment analysis task than is relevant for a topic modeling task. So that's a very quick introduction into what natural language processing is. Now let's start thinking about the tools that we actually need to build these processes. The Natural Language Toolkit is the most utilized package for handling natural language processing tasks in Python. Usually called NLTK for short, it is a suite of open source tools originally created in 2001 at the University of Pennsylvania for the purpose of making building NLP processes in Python easier. This package has been expanded through the extensive contributions of open source users in the years since its original development. NLTK is great because it basically provides a jump start to building any NLP process by giving you the basic tools that you can then chain together to accomplish your goal, rather than having to build all those tools from scratch. A lot of tools are packaged into NLTK, and the next section will dive into downloading the package and exploring some of those tools. Let's jump into actually getting the Natural Language Toolkit set up on your computer. Now, I've linked the instructions to install it down below on either a Mac or a Windows machine, but I took these instructions directly from the NLTK website. Both sets of instructions do assume that you already have Python installed. Feel free to visit this install link here on the NLTK website if you'd like to read a little bit more about NLTK, but you don't have to visit that link to download anything for the installation. Now, if you're on a Windows machine, go ahead and follow the instructions listed here, or if you're on a Mac, you can just follow along. Let's switch over to the terminal. Now we're going to type in here pip install -U NLTK, and that'll just instruct the machine to install this NLTK package. We'll run that. And now, if you already have it installed, you'll see exactly what I'm seeing here. If you have an older version of NLTK, it will automatically update for you. And if you don't have it installed at all, it'll take a few minutes to install. Now let's try and open up Python just to make sure that this is installed correctly. So I'll just type in Python directly here. Then you can type in import NLTK to import the package. And if it doesn't throw an error, then that means you're fine. Let's switch back over to our notebook and explore this package a little bit. Now we'll start by simply importing and then downloading the data to explore this package a little bit. Now we have to add this download step here because NLTK includes all kinds of corpuses and functions, and it actually downloads some of this to your local computer. So if you're ready to run this, if you're new to Jupyter Notebooks, you can just hold Shift and push Enter to run the cell. Now, when you run this, it's going to open a new window asking what you'd like to download. If you already have it downloaded, you'll see exactly what I see here, where it just indicates that all parts of the package are already installed. Now, if you don't have it installed already, what this allows you to do is pick the parts of the package that you would like to have installed. So you'll just highlight what you'd like, and in our case, you should install all of them. So you would highlight all of them, click the download button, and you're going to give it a few minutes. It typically takes 3 or 4 minutes to install everything. Once it's all done installing, then you have to go ahead and close this window, and that'll let NLTK know that you're done installing what you need and you're ready to use the actual package. So let's switch back to our notebook and we'll take a look at what's actually contained in this package. So we'll do dir parentheses NLTK, and that'll print out all the functions and attributes and methods within this package. So this list is incredibly long. We won't have time to explore 99% of these. So I strongly encourage you to start to dive into some of these just to learn what NLTK is capable of. It's a really powerful package. Now I'll call out just a couple of things outside of what we're actually using in this course. So if you find this POS underscore tag, now if you recall back in the slides in the last lesson, I mentioned part of speech tagging is one component of natural language processing. So this is the actual function within the natural language toolkit that will actually do that for you. So we're not going to use that in this actual class, but it is a useful function to know, and I would encourage you to explore using that. The other function that I want to call out is the tokenize function. Now this will just take a sentence and split it into a list of words that makes it easier for Python to digest what it's supposed to be looking at. Later in the next chapter, we're going to actually tokenize ourselves, but we're going to build our own function to do it. And the only reason I did that is so that you can better understand what's actually happening under the hood and how this actually works. Moving forward, you can feel free to actually just use this function to do it. It's much faster than building your own function to do it. Now let's dive in and actually experiment with one small component of NLTK. So we're going to take a quick look at some stop words, just as an example to see how you call certain things from NLTK. We'll learn what stop words are a little later on, so it's not important to remember that specifically. So we'll start by telling it that we want to import stop words from nltk.corpus. So from nltk corpus, import stop words. And then to actually look at the list of stop words, we'll type in stop words and then tell it we want the actual words there. And there are stop words in different languages, so we'll tell it that we want the English stop words. And it's a fairly long list, so we don't want to look at the whole thing. So we'll just print out the first 10. So we'll see I, me, my, myself. So it's a lot of pronouns here. So let's take a look further down the list. What we're going to tell Python to do is start at the 0th element, or the element in the 0th position, and go up through the element in the 500th position, and we only want it to print out in increments of 25. So we'll run that, and you'll see it's not all pronouns. There's also been, with, here, very, things like that. Again, we'll get into this in more detail later on, so it's not necessary to remember this now. But stop words are basically words that are used very frequently, but don't really contribute much to the meaning of the sentence. For instance, you may be trying to do some sentiment analysis, and these words are generally sentiment neutral. So there's no strong meaning necessarily one way or the other. They're just clouding the signal and taking room away from words that aren't sentiment neutral. So we can go ahead and safely drop these. Again, we'll be digging more into this later on, so it's not important that you know exactly what stop words are. Just that it's useful to see how you can access a specific corpus of words in NLTK. So this was a very quick introduction and high-level overview of some of the attributes and methods contained within the NLTK package. We'll get into more detail as we move forward in this section. Now that we've learned the basics of what NLP and NLTK are, we're going to continue the process of assembling some tools and knowledge that we'll put to use as we move forward in this course. In this lesson, we're going to learn how to read in semi-structured data. This probably isn't something you really think about if you're used to reading in well-formatted CSV or Parquet files in the past, which would be represented by this nice columnar or row-based depiction on the left. But reading in text files can be a little bit of a battle sometimes, represented by this figure on the right. Text data will typically be in a semi-structured or unstructured format. So I've mentioned unstructured a couple times. What does that really mean? Well, it could mean that it's binary data, it could mean no delimiters, or it could mean no indications of any rows. A few examples might be an email, PDF file, social media posts. These may just get dumped into a file with no indication of where maybe a subject of an email ends and the body of the email begins, or even where one email ends and the next begins. It could also get cluttered by things like HTML tags, and we won't really get into it in this course, but the idea is just that it can get really messy. It's important to note that Python is pretty smart, but ultimately, unless it's told otherwise, it basically sees everything as a string of characters. It needs to be told what those characters mean. So to illustrate how to read in semi-structured data, we're going to be using a data set from the UCI machine learning repository. This data set is a collection of text messages, each with a label of either spam or ham. We'll be using the same data set for the duration of the course, and it's all contained in your exercise files, so there's no need to download it. Now, before we dive into this, I want to show you what the raw text file looks like so we know what we're working with. It's not a clean CSV file, but it's not terribly unstructured either. Each row has a distinct text message and a distinct label as either spam or ham. So in the context of text data sets, this is actually pretty well structured, so this shouldn't be too difficult. Now let's jump back to our notebook. So we're going to start by opening this file and just reading it, which basically just means that you're pulling in the text without any semblance of structure at all. You may do this if you don't know what your data looks like and you're just reading it in. This gives you a way to get a first look at the data, and then you can determine your next step. So we're opening it and then we're reading it. I should note that this lesson is as much about text manipulation as it is reading in a file. The way we'll read this in certainly isn't the easiest, but many times you don't know what the easiest way is up front, and you have to explore the data first. Additionally, I don't want to limit you from taking on more complicated data sets moving forward, so we're going to take a roundabout, inefficient way to reading this with the purpose of arming you with some tools that you'll need to take on more difficult data sets later on. So we've read in our data set using this open.read. Now let's print it out and take a look at what's contained in here. So because we've read it in without any indication of format, it doesn't know if there are rows, columns, words, or anything. All Python sees is a very long string. So to tell it how much to print out, we basically just tell it how many characters. So we're telling it print out the first 500 characters. So now you could see that it's just basically a block of text, and you'll see that you have these \t and these \n separators. The \t's are between the labels and the text message bodies, and the \n's are typically at the end of those lines. There are many ways to tackle this. The way that I'm going to do it is replace the \n's with \t's, and that'll allow us to split this into a list, and then we can split it up from there. So what we're going to do is we're going to assign this to a list called parse data, and we're going to pass in and say we want to use this raw data string, and what we're going to do is we're going to use this replace function. What that's expecting to see as the first parameter is the thing that's looking for. In this case, that's \t, and then the second parameter is what it's going to replace that with. In our case, we're going to do \n. So every time it sees \t, it'll replace it with \n, and what this allows us to do is then do .split. And what this will do is it'll take our string and split it on a certain character and return a list. So we'll tell it split on \n. So now every time it sees an n, it'll chop it off and add that component to a list. So if we run this, and then we'll print out parsed data. Instead of printing out the first 500, now it's an actual list. So we'll just print out the first 5. Now you can see that this is basically alternating, where your labels exist in your 0th position, the 2nd position, the 4th position. So it's every other, and the same thing with the actual labels. So this gives us some sort of structure. So what we're going to do is we're going to create a new list called label list. And what we're going to do is we're going to pull from that parsed data list every other item. So what we tell is parsed data, and we want to start in position 0. So that'll be the very first one. And then we tell it we want to go to the end, so we don't enter anything in the second place. And then we tell it 2. So what that's telling it is start in the 0th position, go to the very end, and take every other. So it'll grab ham, spam, ham, and so on. Now we want to do the same thing for text lists so that we can get the text bodies in a different list. So again, we're taking parsed data, but this time it's going to be starting in the position 1, which is the second element in the list. So it'll start with this one, and then it'll grab every other one. So we'll run that, and then let's take a look at the first 5 entries of label list, and then we'll take a look at the first 5 entries of text list just to make sure that it did what we expected it to do. And we'll go ahead and print both of these, because if you don't include the print statement, Jupyter Notebooks will only print the most recent statement. So it would only print text list and it wouldn't print labeled list. So we'll add the print statement on both, print those out, and we can see the lists are separated in the way that we expected them to be. So now we have the information that we need separated into two lists. So now we can start thinking about combining these in a way that we can actually use for analysis. The first thing we have to do is import pandas. So just do import pandas, and we're going to save that as PD so we don't have to call pandas every time that we need to use one of its functions. And we're going to create a data frame that we'll call full corpus. And the way that we create this data frame is PD dot call the data frame method. And within this data frame parentheses, we're going to need to pass it a dictionary, where in the dictionary, the keys are going to be the name of the columns, and then the values will be the lists that we've stored the actual values in. For the first column, we'll call it label, and we'll pass in label list because that contains the actual values. And then the second column we'll call body list, and we'll pass in text list. So what this should create is it'll take label list, text list, create a data frame out of them, and then label the column names label and body list. So let's go ahead and print this out. Full corpus.head, that'll print out the first 5 rows. And we have an error. So it throws an error saying the arrays must have the same length. So let's dig into that. So we're going to check the length of each of these lists to see where the issue lies. So do print len label list to print the length of that list, and then we'll do the same thing for the text list. Print those, and you see that label list has one extra entry that text list does not have. My guess is it picked up on something at the very end that is creating the mismatched length. So let's print out the last 5 items of label list. So the way we print out the last 5 items is we do -5 till the end. So what that'll say is go to the very end, count 5 backwards, and print out those last 5. And you'll see that the very last entry here is empty. So it is picking up on one extra entry that we don't need it to. So if we just drop that, then it'll have the same length as text list and they'll match up. We can just copy this code from here because we're going to be using the same exact thing to create our data frame. The only change we're going to make is we're going to tell label list, instead of grabbing all of them, just don't grab the last one. So this says start at the beginning and capture all of them except for the very last one. So now when we do full corpus and print out the first 5, that should print out the way that we expect. And so now you have a nice clean version compared to what we had over here where it was rather messy and you could see some structure, but now we have it all cleaned up where it's all in the data frame, and you can start to see how you could actually do some analysis with this. Now, I'd like to revisit the fact that I mentioned we would take a bit of a roundabout way for the purpose of arming you with the tools to tackle more difficult data sets. To give you an idea of where we could have taken a shortcut to reading this in, as soon as we notice the \t up here, that tells us immediately that this is tab delimited. Pandas allows you to read in tab-separated files very easily. You'll learn that different details like this \t are giveaways to allow you to take shortcuts essentially to reading in your data. The easiest way to actually read this in will be to use the read CSV function from pandas. So we'll assign this to dataset and we'll call pandas.read CSV, and we just pass in our spam collection data set. And the thing that tells it that it's spam separated is there's a separator parameter here, and we tell it \t. So that tells it that it is tab separated. And the only other thing that we need to add in here is header equals none. The reason we need to do that is because the raw data set does not have column names. And if we don't say header equals none, it'll take that first column and assume those are column names. So let's go ahead and print this out. And as you can see, the column order is switched, but it's the same content and there's just no column labels here. So in this lesson, we took a data set where we didn't have any idea what the structure was, and we explored it to uncover the structure of the data set and organized it in a clean way. So now it's prepared for the next steps in our NLP pipeline. In the last lesson, we learned how to read in our data set the difficult way to arm ourselves with some text manipulation tools, and then we learned the easy way using Panda's read CSV function. Now we're going to read that data back in the easy way. So again, we're importing pandas and storing it as PD, and then we're calling pd.readCSV, where all we have to do is pass in the name of the data set, so that's SMS spam collection.tsv. And then we have to explicitly tell it what the separator is. So we tell it \t, which indicates tab separated. And then lastly, we tell it that it shouldn't expect a header. In other words, if we don't include this, it'll just take the first row as the column names. And then we're storing that as full corpus. Now, as we saw in the last lesson, there won't be any column names. So let's go ahead and actually tell it what to name our columns. So let's call full corpus.columns, which just stores the column names. And then we can just simply pass in a list. So we want the label to be called label, and then we want the text message to be called body_text. Now let's go ahead and just print out the first 5 rows of this data frame. There, it looks like just what we saw last time. Now, typically before diving into any in-depth analysis, data cleaning, or model building, we want to do some very high-level exploration of our data to understand what we're working with. So we might ask questions like, what is the shape of our data? How many ham or spam are in our data set? And are there any missing values? So this will inform the decisions that we make as we move forward. So let's start by shape. So this will help us understand how much data we have to build a model on and how many columns there are. To make this clean, we'll use print statements so that we can say input data has this many rows and this many columns. And then in order to fill that, we just have to do .format, and then we pass in the number of rows, which is filled simply by len full corpus, and that'll fill the first bracket. And then for the second bracket, we just have to do len full corpus dot columns, just like we assigned above. So then when we run that, it'll just tell us how many rows we have and how many columns we have. So for this data set, it's pretty obvious because we can just count the number of columns, but it's more important as you have a couple million rows and hundreds or thousands of columns, you won't really be able to count the number of columns. So this can actually be pretty helpful. Next, we want to know how many rows are spam and how many are ham. This is especially useful as we move towards machine learning. If something like 5,560 out of the 5,568 are spam, then we would approach this problem in a very different way than if it were a 50-50 split. So we're going to use the same format for the print statement as we did previously. So here we'll say out of this many rows, this many are spam, and this many are ham. And then again, in order to fill those brackets, we just do .format. And for the number of rows, it's the same that we did before, len full corpus. Now, in order to get how many spam we have in our data set, we'll go to a new line, and then again, we're still going to take the length, but we'll take full corpus, and then we need to filter the full data set to only include the rows where the label is equal to spam. And then we'll close off our length parameter. So again, what this is doing is it's taking the full corpus data set and it's filtering it to say the rows must have label equal to spam. And so that'll filter the data set down to only rows that have label of spam, and then you take the length of it, and that'll tell you how many of your text messages are labeled spam. So now we need to do the same exact thing for ham. So we can just go ahead and copy this filter statement that filters on spam, copy it down to the next line, and all we have to do is change this from spam to ham. So now this will filter your data set down to only the rows or text messages that have a label of ham. So let's make sure that all our parentheses are aligned. So just add one more parentheses to close out your print statement. And then you can run this and it tells you out of 5,568 rows, 746 are spam and 4,822 are ham. This is fairly lopsided. This is important information as you're starting to build your machine learning classifier. And even later on when we start creating features, this will be useful to know. So we'll revisit this again in the feature engineering chapter. Now, lastly, we want to understand how much missing data there is. If we have text that's missing, then we won't really be able to use it to build a model if we're missing the actual body text. So we want to know that ahead of time. So again, we're going to use the similar format with the print statement. And this one will say number of nulls in the label and have that bracket. And then again, we do format. And in order to get the number of nulls in label, we just do full corpus label. And then we can use this isNull method. And what this isNull method will do is it'll look at the entire column of labels and return a true or false for every single one. So if label is present, if there's either spam or ham, then it's false because it is not null. And if it is missing or it is null, then this will return true. And then what we can do on the end of that is add .sum, and that .sum will just sum up all of the trues. So that will return how many nulls there are in label. Now we want to do the same thing for the text body. So we can just copy this where we did isNull for label down here, and we can just change this from label to text. And then we change the column that we're calling this on from label to body text, but we'll run the same thing isNull. It'll look for nulls and assign a true if it is missing. And then we sum up all the trues. So we can run that, and luckily we don't have any missing values, which is going to be really helpful. This lesson helped us better understand our data once we actually got it read in. The insights pulled from this very basic exploration will help dictate how we approach the rest of our data cleaning and model building. Now that we know how to read in messy text, we want to learn some basics for how to manipulate, search for, or split that text. So in this lesson, we're going to cover some basics on regular expressions. If you're new to regular expressions, a regular expression, or regex for short, is a text string used for describing a certain search pattern. So if you're familiar with wildcards for search, like if you wanted to search for any CSV file on your computer using star.csv, this is basically just a supercharged version of that. Regular expressions can take various forms that we'll experiment with in the next lesson, but to give you a very quick example of what I mean, this regular expression will just search for the explicit NLP string within some other string. This isn't so much a search pattern as it is an explicit command for what we want to find. So if it was I love NLP, then this search pattern would just capture and return NLP. Another way to identify that NLP string would be to use this expression. And this will just search for all single characters between J and Q in whatever text we're looking at. But this will search for all characters between J and Q, not just N, L, and P. The other consideration here is that this will only return single characters at a time. So this would return N, and then L, and then P, and also whatever other characters between J and Q in your text string. This isn't usually what we're looking for. So we can solve that issue of only returning a single character by simply placing a plus sign outside of our brackets. What that will tell Python is that it can search for strings longer than one character. So what this will look for is any character between J and Q, just with the added flexibility of returning strings of multiple characters together that are between J and Q. Switching gears a little bit, this one will return all numbers with the flexibility of returning sequences of more than one number. So if there's a year, like 2017, it will return the full year rather than each number individually. And then lastly, to combine these two concepts, this will search for sequences of characters between J and Q or numbers between 0 and 9. So if you had a course name that was NLP 2017 without any spaces, then it would return that full string. But if you had NLP 2017 with a space in between them, then that would return them as two separate sequences. This is just 5 very quick examples, but there's literally an infinite number of patterns that you could come up with, and regexes give you the power and flexibility to search for almost any kind of pattern you could imagine. The examples are useful, but why do we actually care about this? Regexes are particularly useful when dealing with text data because a lot of the data is unstructured, where you need to be able to use these patterns to try to create some structure within the document. For instance, you could use a regex to identify the white space between words or tokens, or even let Python know how to split up a certain sentence. Another use is to identify delimiters between columns or end-of-line escape characters that indicate the end of one line and the beginning of another, like we saw in our SMS spam collection dataset. They can also be used to remove punctuation or numbers, clean HTML tags, or just identify some random patterns that you're interested in. A few examples of regular use cases might be confirming passwords that meet some criteria. So maybe a company requires one capital letter, one lowercase, and one special character in their passwords. You can create a regex to confirm that each new password created matches that criteria. Then the last three all kind of fall under the same broad category of searching for a certain pattern, like file names, so find all the CSVs that meet this criteria, or some portion of a URL, so maybe it's whateverfollows.com or .org, or scraping for key information from a larger document like package version numbers from a technical report. There's a lot to unpack with regular expressions. I'm going to outline a few quick examples here, but there's so much that you can do with regexes in terms of searching for character patterns, character placement within a string, splitting up the strings, and so on. So I encourage you to do some of your own exploration to learn the different patterns and the functions that can be used. You can find more details in the link here. To put this to use, the low-hanging fruit here, and the primary reason that we're talking about regexes, is in order to tokenize sentences or split a sentence into a list of words so that Python can understand what it needs to be looking at. Right now, Python just sees a string of characters, so we need to tell it what to focus on and how to organize those characters. For our machine learning model, Python will need to split the string into what we call tokens or words so that the model can learn how those tokens relate to our response variable. So we're going to use this re package, which provides a lot of the functions that we use along with regexes. So we will import re here, and then we have three test sentences here that we're going to use to test these regular expressions. All of the tests are a sentence that just says this is a made-up string to test two different regex methods. The first test string is pretty clean, and then the last two are a little bit messier where I've inserted extra spaces and special characters. And so we're going to use these three test cases to thoroughly test each regex to see if it works through a range of scenarios. It's worth noting that these are sentences you really could run into on a job. It's not all that uncommon to have random spaces or special characters dispersed throughout your text, and you'll need to be able to deal with that. So let's go ahead and run this cell. The first thing we're going to work on is using two different regex methods to split a sentence into a list of words. The first approach that we'll take is using the split method from this repackage. The goal in using this method is to identify the white space or characters separating the words and then tokenize your sentence in that way. So here's how we're going to do that. We're going to start by testing this split method on our first test string, which is the cleanest of the three. So we'll do that by typing in re.split, open parentheses, \lowercase s, comma, and then the name of the first test string, which is re_test. Now what this \lowercase s tells Python to look for is a single white space to split the string. So let's run that, and on the first test string, you could see it's pretty clean, and so looking for only one single white space works pretty well on that. But let's go ahead and try this on the second test string. So we can just copy this code directly down here, and then all we have to do is just add _messy at the end. And let's run that, and you can see that this is not quite as clean as the previous one. Python doesn't know what to do with these extra white spaces that are included because this is only looking for a single white space. So a regex this simple won't work. So if we copy this on down to the next cell, so we can just add a plus sign after the S here, and that will tell Python to look for one or more white spaces. So it should be able to handle this case where we have multiple white spaces. And we're going to run that on the second test string again. And you can see that that handles it pretty well. The real test is going to be on the last test string where it has special characters separating the words. So let's add 1 to the end of re_test_messy and run that same regex on that last one. You can see that it doesn't split it at all. It just returns the entire string all as one. When dealing with special characters as the separators between words, this simple regex can't handle that scenario. So searching for white space isn't quite robust enough to handle the more complicated strings. So let's try a regex that's a little bit more flexible. So we can just copy this most recent example that we're using. So instead of using \s plus, we're going to change that to \W plus. Now what this regex will do is it'll search for any non-word character, and it'll use that to define its split. So whether it's a space, a \, quotes, period, anything, it doesn't care. And we're going to keep this plus sign in there because we know that our string has more than one special character in a row. And if we remove that plus sign here, it won't be able to handle multiple special characters in a row. So we keep that plus sign and we can run this, and you can see that it works well on this most complicated version. And I'm not going to test it, but we could back test it against the prior two examples, and it would work well on those ones as well. So as a recap, using this split method allows us to tokenize by finding the characters that separate the words. The other option is, instead of searching for what splits the words, just search for the actual words themselves and ignore the characters that split the words. This can be done using the find all method. The nice thing about this method is it's the same syntax as the split method, so we'll just have to change the regex that we're using. So I'll copy this, add a cell down below, copy that in, change re.split to re.findAll. And then we're going to change our regex from \W plus to \S plus. We saw that using \lowercase s plus looked for one or more white space characters. Now when we capitalize that s, it will flip it. Instead of looking for one or more white space characters, it looks for one or more non-white space characters. So we get the opposite effect. So let's start by testing this out on the most simple example. So we'll test it out on re_test. And you can see that it does well on that most simple example that's just separated by single white spaces. Now let's copy that code down, and we'll run it again on the second example, which is just adding _messy. So this is the one that has multiple white spaces separating the words. And it still does well on that one. So let's test it on the most complicated one where we have the special characters separating the words. So we'll just change re_test_messy to re_test_messy1. And we'll run that, and it cannot handle this scenario still. Because it's still looking for non-white space characters, the dashes and backslashes and periods still count as non-white space characters. So it still thinks those are part of the word. So we need a more flexible regex. So let's copy it down here, and just like we did before, we're going to switch from using S's to W's. Previously, we learned that W plus looks for one or more non-word characters. So again, by making it lowercase instead of capital, it flips it. So this will search for one or more word characters. So basically, it'll search for tokens that resemble a word. So it'll actually look for letters. So let's run this on the most complicated example and see if that works. It does return all the tokens that we're looking for. So again, it'll search for the actual words, ignore all of these special characters, and it'll properly tokenize our string and return only the words that we care about. So that's how we can use two different methods from the re package, along with several different regexes, to properly tokenize messy sentences. Now that we've covered some of the basic regex usage for the purpose of tokenizing, there are a few takeaways to keep in mind. There are two methods from the re package that can be used for tokenizing. Find all will search for the actual words while ignoring the things that separate the words, while split will search for the characters that split the words while ignoring the actual words themselves. And the regexes that are most useful for tokenizing, keep in mind that anything using a W is based on words, while anything with an S is based on white spaces. In our daily work, it's much more common to be using the W regex because it allows the flexibility for words to be separated by spaces or special characters. But having an understanding of what the S offers you is a nice tool to hold in your back pocket. Picking up right where we left off, understanding how regexes can be used for tokenization is helpful, but let's explore another usage of regexes. So I've defined a sentence here. I want to follow PEP 8 guidelines. If you're not aware, PEP 8 is a style guide for Python. Now let's just say this sentence lies in some very large document that you've put together, and you realize that a lot of people don't know what PEP 8 means. So you want to expand it to PEP 8 Python style guide. However, let's assume that it's also likely that you made some spelling errors. So instead of PEP 8, maybe you had PEP 7 or PEEP 8, which are represented by these other two test strings. So you don't really feel comfortable explicitly searching for PEP 8 and then replacing that with PEP 8 Python style guide because you'll miss these mistakes. So you need to come up with a pattern that will not only capture PEP 8, but also your mistakes. So we want to build a process that will identify every place where PEP 8 occurs, plus some likely typos, and replace it with PEP 8 Python style guide. So what we're going to do is we're going to use the findAll function that we learned in the last lesson, and we're going to test what will find PEP 8, and then after we find the proper regex, we can use a sub method to replace it. So let's run this first cell to store our test strings. And then in order to actually test this, we're going to have to import the repackage that we've used previously. And then we need to call the findAll function. So that's going to be re.findAll, open parentheses, and the regex that we're going to use is open bracket, lowercase a, dash, lowercase z, close the bracket, and then add a plus sign outside of it. And then as the second parameter, we're going to pass in PEP 8 underscore test, which represents the first test case that we laid out above. So let's go ahead and run that, and it returns try to follow guidelines. So try to follow and then guidelines. So you notice the thing that's missing is PEP 8 and I. So what that indicates to us is that the regex is case sensitive, and it's only looking for lowercase a through lowercase z. So let's make that change and just change this to capital A and capital Z. So this again will search for strings of one or more characters with capital A through Z. So let's run that on our first test case, PEP8 underscore test. And it captures I, and it also captures PEP, but it doesn't get the 8 in there. So if you recall the slides that we saw earlier in this chapter, we added 0 to 9 within the brackets here. But what that did is actually search for letters or numbers. So it would still capture the I, and it would also capture any other number in this document. But for PEP 8, what we want it to do is capture letters and numbers. So the way that we can do that is adding a bracket around A to Z, and add a plus sign outside of that, and then add a bracket around 0 to 9. So now what it'll search for is strings of one or more characters with letters A to Z capitalized and number from 0 to 9. So let's go ahead and run that, and you see it'll capture PEP 8. Now let's just run through our other two test examples really quickly. So let's test it on PEP 7 test, and it captures PEP 7. And lastly, let's test it on PEEP 8 test, and it captures that. So this regex pattern is properly capturing PEP 8 along with two other likely misspellings. Now that we have the proper regex, the second part of this process is to replace the tokens captured by this regex with PEP 8 Python style guide. So for this, we're going to use the sub function, which will search for a regex pattern, and then when it finds it, it'll replace it with a given string. So the way we actually implement that is re.sub. So we'll pass in the regex that we defined above, a-c, close bracket, plus sign, new bracket 0 to 9, with the plus sign outside of the bracket. And then we'll say when you find that, replace it with PEP 8 Python style guide. And then lastly, we have to tell it what string we want it to test it on. So we'll test it first on PEP 8 test. So just as a reminder, what this should do is find PEP 8 or PEP 7 or PEEP 8 and replace it with PEP 8 Python style guide. So let's run that. If you take a look at what PEP 8 test originally was, it simply just added Python style guide to the end. So let's test this now on PEP 7 test and see if it still does that appropriately, and it does. So instead of PEP 7, it's now PEP 8 Python style guide. And lastly, we'll test it on PEEP 8, and it does the same. Now, this regex certainly isn't perfect. You can imagine a scenario that it would miss. For instance, if there's a space between PEP and 8, or if it was lowercase, it would miss both of those. So you'd likely need to spend some time refining your regex. However, the point is to illustrate how you can use regexes and give a practical example of a case that you might use it in. So now up to this point, we've explored 3 different regex methods with some practical application of how you might use it. But there are a lot of other regex methods within this re package. A few are listed here. So there's search, match, full match, find iter, and escape. Even more broadly, the regexes that we explored are very, very simple. They can get very complex, and the best way to learn it is by defining your own string with the goal of identifying some substring, pull up a regex cheat sheet, and just start exploring different patterns to try to identify that substring. Up to this point, we've learned some basics of NLP and NLTK. We've learned how to read in messy text, and we've learned how to use regular expressions to search for and manipulate that text. In this lesson, we'll take a step back to understand how this all fits together in the broader machine learning pipeline before we dive into each step individually. This lesson is going to introduce some new topics as well, but don't worry, we'll cover each of these topics in later lessons. This is meant only to provide the proper context for how this all fits together. In a typical machine learning text pipeline, you'll start with some document with raw text in it, like the SMS dataset that we're working with. It's important to note that at this stage, the computer has no idea what it's looking at. All it sees is a collection of characters. It doesn't know the word ham from the word spam. The characters mean nothing. It doesn't even know a space from a number or a letter. They're all the same. So the first thing we need to do is tokenize our text. We did this earlier in this chapter by splitting on white space or special characters. So you would take the sentence, I am learning NLP, and it would split into a list with 4 tokens. I, and then am, and then learning, and lastly NLP. So now instead of just seeing one long string of characters like it was seeing before, now Python will see a list with 4 distinct tokens so it knows what to look at. So now we have a list of tokens, so Python knows what to look at, but some of the words might be a little bit more important than other words. For instance, the words the, and, of, or appear very frequently but don't really offer much information about the sentence itself. These are what's called stop words. We took a quick look at these earlier in this chapter. Typically, you will remove these words to allow Python to really focus in on the most pivotal words in our sentence. So in the example I used previously, instead of a list with I am learning NLP, once you remove stop words, now you're just left with learning and NLP. This still gets across the most important point of the sentence, but now you're only looking at half the amount of tokens. Also, the process of stemming helps Python realize that words like learn, learned, and learning all have basically the same semantic meaning. You may not think this is a big deal, and in a small sample it's really not, but when you all of a sudden have 1 million text messages and a corpus of 150,000 words, any words that you can remove to allow Python to focus on the most pivotal words can really make a big difference. Okay, so now Python sees a list of tokens you care about and the key words that we think are useful for building some kind of machine learning model. Even though Python now knows what you care about, it still only sees characters. It doesn't know what learning or NLP even means. So now we have to convert it to a format that a machine learning algorithm can actually ingest and use to build a model. This is a process called vectorizing. We'll talk about this in more detail next chapter, but it's basically converting the text to a numeric representation of that text, where you're essentially counting the occurrences of each word in each text message using a matrix with 1 row per text message and 1 column per word. Again, don't worry about fully understanding this right now. We'll cover this in much more detail in the vectorization chapter. So now that you have this numeric matrix, you can now fit your actual machine learning model by feeding in your vectorized data along with your spam or ham labels. The model will then learn the relationships between the words and the labels in order to train a model to make predictions on text messages that it has never seen before and determine whether they are spam or not. There are various types of machine learning models. It will be up to you to select a few of them to try out. You'll tailor your choices based on the type of input data you're giving it, what you're trying to predict, how much compute power you have, things like that. You'll typically test out a number of what's called candidate models before selecting which model performs best. Once you select the best model, You'll evaluate that on a holdout test set, and this is typically a set of data that you'll set off to the side in the very beginning for the purpose of testing your final model on it to see how your model will perform on data that it's never seen or touched before. If it passes this final test, then you'll prepare to implement it within whatever framework you're working with. In this example, it's an illustration of a spam filter trying to filter out whether incoming email is spam or not. If you're not familiar with a typical machine learning pipeline, this can be a little bit confusing. Don't worry though, it'll make more sense as we deep dive in each topic through the next few lessons. Let's jump into actually implementing steps 2 and 3 in this pipeline. We've talked about a few different concepts throughout this chapter. In the last lesson, we put those together at a conceptual level, laying out what a full machine learning pipeline looks like. In this lesson, we're going to actually write the code to handle the cleaning portion, or the pre-processing as it's typically referred to, of this machine learning pipeline. These are 4 steps that you'll see in a lot of text cleaning pipelines: removing punctuation, tokenization, removing stop words, and lemmatizing or stemming. We're going to focus on the first 3 steps in this chapter. Then we'll cover lemmatizing and stemming in the next chapter, as those are a little bit more advanced and not implemented in every pipeline. So the beginning of this script will ingest some raw text, and by the end, we'll have text that's all cleaned up and prepared for the vectorization step laid out in the last lesson. It's worth noting that there are custom packages to do most of this for you, like that tokenize function that we saw from NLTK earlier, but I want to walk through this step by step to illustrate how the system works under the hood. So we'll first read in our data. We'll use the same SMS spam collection data set that we've been working with. We'll need pandas to read in this data, so we'll go ahead and import it here. And then we're going to do something new by setting a custom value for how many characters we can see in a pandas data frame when we print it out. So we do this by simply calling PD, which refers to pandas, dot set option, and then the option that we're passing in is display dot max call width, and then we pass in 100. Again, the default here is 50. We're just changing it to 100. So now we're going to read in the data using the pandas read CSV function that we've seen before, indicated that it's tab separated and that there's no header. Then we'll define the column names, and we can go ahead and run that, make sure it prints out properly. So you'll even notice here that this is printing out much more of the actual text message that we saw previously because we widened the column. Before we dive into cleaning up this data set, I want to quickly show you where we're trying to go with this. So I went ahead and cleaned up this data set ahead of time, and I'll read that in just to give you some direction and understanding of what we're working towards. So I'll just go ahead and run this cell. Now you'll notice that the body text column is the raw text that we saw above, and then the body text no stop column is the cleaned up version. So there's no punctuation within the words. They're all split into tokens. You'll see that all the stop words are removed. For instance, just looking at the first row, you'll notice that Ben is gone. You'll notice that for and the are gone. They're not present in this list over here. So this is where we want to get to, and over the next couple lessons, we'll piece together the tools that we need to get this cleaned version. So now we have a decent idea of where we're going. The first step we're going to take is to remove punctuation. In order to remove punctuation, we have to have a way to actually show Python what punctuation even looks like. Luckily, the string package has a list of punctuation in it. So we'll go ahead and import string, and then all we need to do is just call string.punctuation, and we can run that, and that'll just print out a list of different punctuation. So this is really helpful to allow Python to identify what we're looking for here. The reason that we care about this is that periods, parentheses, and other punctuation look like just another character to Python. But realistically, the period doesn't really help pull the meaning out of a sentence. So for instance, for us, I like NLP with a period is exactly the same as I like NLP. They mean the same thing to us, but when you give that to Python, Python says those are not equivalent things. And Python isn't saying I like NLP without a period is different from I like NLP with a period, in that they're really close, but one has a period and one doesn't. To Python, these might as well be I like NLP versus I hate NLP. It knows they're different without any ability to understand how different they are. In order to clean this up, we want to take this list of punctuation and tell Python basically, whenever you see anything like this, we want you to remove it. So we're going to build our own function to remove this punctuation. And conceptually, what we want Python to do is cycle through each character, check if it's some kind of punctuation. If it is punctuation, discard it. And if it's not, then keep it. So we're going to use list comprehension to develop that functionality. List comprehension makes it easy to cycle through elements, check if they meet some condition, and then just return if they do meet that condition. So let's go ahead and build this function. So we're going to call it remove punct and open close parenthesis, and within that we're going to pass in some text. So that's what it expects. Now we need to build our list comprehension. So I'm going to walk through the actual what we're going to type here, and then I'll revisit it and explain the actual syntax. So what we're going to type in is char for char in text if char not in string dot punctuation. And we'll just all assign this to text underscore no punct. In terms of the syntax of the list comprehension, let's focus on just the part that I've highlighted so far. So we're saying char for char in text. So what this is saying is for the text that we passed in, return each character for each character in this text that's being passed in. So what this will do is it'll create a list where it'll just store a character in each element of that list. Now, the condition that we're really concerned about here is we want to make sure that that character is not punctuation. So now this entire thing is saying return the character for each character in text as long as that character is not in this string of punctuation. So this text underscore no punct will be a list of characters that are not punctuation. So we need to return text underscore no punct. And then in order to actually apply this to our data set, we're going to use what's called a lambda function. So first, we're going to define the name of the column that we want this clean data to be passed into. So we'll call it body underscore text underscore clean. And then we'll set that equal to the column that we want to call this function on. So we want to call this remove punct function on data body text. And then in order to apply the lambda function, what we do is we type dot apply lambda x remove underscore punct x. And so what this will do is it'll apply this function that we just wrote to each element or each row of body text. And so that'll remove all the punctuation and then return it as a column called body text clean. So let's just print out the first 5 rows of that and run it. So it returns each character individually. So this is actually expected behavior since we told it to return a character. And we do need to check each character. So this is a reminder that list comprehension will return a list, and because we explicitly told it to evaluate each character to see if it's in the list of punctuation, when it's done checking, it'll just return that as a single element in the list. So in order to fix this, we're going to wrap this in a join function. It'll take this list that this list comprehension is generating, and it will just join each individual element to one another. And you'll notice if you just join I with the V, with the E, and then space, and then B, it'll recreate our original sentence. Now the only catch is this join function needs to know how it's joining these things together. So if I indicated a space there and hit dot join, what that would do is it would create I space V space E. So what we want to tell is join it on nothing, basically. We don't want a space in between them. So this will recreate our sentence. So if we go ahead and run that, now you can see that now it's joined right back together as a sentence. So that is how you remove the punctuation from a string. In the next lesson, we'll pick back up right here and learn how to split the string into a list of tokens. Let's jump in where we left off previously. If you're just joining us, go ahead and rerun all the cells prior to this tokenize heading. Now that we've removed punctuation, we can move on to tokenizing our text. As we've discussed previously, tokenizing is splitting some string or sentence into a list of words. We learned that you have to account for edge cases in your strings, like if they're separated by special characters or multiple spaces. So we'll just use what we learned in our lesson about regexes and combine that with the approach we learned in the last lesson, where we removed punctuation by writing our own function and then applying it to our dataset using a lambda function in order to tokenize our text. So we'll use the same repackage that we used last time, and then we're going to go ahead and define our own function and call it tokenize, and it'll accept some text. And so the first thing we're going to do is, again, call this re.split function, pass in the regex that we want to use, which is going to be this capital W plus sign. And then as the second parameter into this split function, we'll just pass it text, which is what's being passed in. And then we need to assign that to something, and we'll just assign it to tokens. And then we will want our function to return that list of tokens. So just as a reminder, this capital W plus regex indicates that it will split wherever it sees one or more non-word characters. So that'll split on white spaces, special characters, anything like that. To apply this to our data set, we now need to use a lambda function just like we did last time. In this lesson, we're going to use the body text clean column that we created in our last lesson. And just like we did previously, we'll use .apply lambda x colon tokenize x dot lower, and that dot lower I'll return to in just a second. So this will take this tokenized function and apply it to each element or each row of body text clean. Now we need to assign it to a new column. We'll call it body text tokenized. So we can go ahead and run that, but let's print out the first 5 rows. Now you see it's taken this sentence and it's properly split each word into its own entry in the list, and they're all lowercase. Now just to circle back to this lower method, this isn't necessary for this function in particular, but it will be necessary moving forward. Now Python is case sensitive, so if you give it capital NLP and ask if it's the same as lowercase NLP, we know to us that's basically the same thing. But if you run that for Python, Python says those are two different things. So when we get into further steps, now Python is seeing capital NLP as something totally different than lowercase NLP. And it has to learn that those things are closely related. But we don't want it to consume its resources by learning that those things are related. We want to explicitly tell it that those are the same things. So that's why we apply this .lower method. So now we have a nice clean list of words without any punctuation. So now Python knows the tokens or components that it's supposed to be looking at. The next step is going to be removing some of the more irrelevant words in these lists. So let's jump in where we left off previously. If you're just joining us, go ahead and rerun all the cells prior to this remove stop words heading. We're almost through the basic cleaning steps now. Thus far, we've removed punctuation and tokenized to create a list of words out of a sentence. The last step in cleaning up this data is to remove stop words. Now, we've discussed stop words previously. There are commonly used words like the, but, if, that don't contribute much to the meaning of a sentence. So we want to remove them to limit the number of tokens Python actually has to look at when building our model. For instance, take the sentence, I am learning NLP. After tokenizing, it would have 4 tokens. I am learning an NLP. Then after removing stop words, instead of a list with 4 tokens, you're now left with just learning an NLP. So it gets across the same message, and now your machine learning model only has to look at half the number of tokens. So we'll use this NLTK package that I introduced earlier, and this has a nice built-in set of stop words. So we'll call that using nltk.corpus.stopwords.words. We have to tell it that we want the English stop words. So we can run that, and now for removing these words, this isn't going to be anything new. So we're going to define our own function, and we'll use the same type of list comprehension we used to remove punctuation above. Now we're just going to use stop words as our exclude list instead of punctuation. And then we'll use a lambda function to apply it. So let's name our function remove stop words, and it will accept a tokenized list. So that's important that what we'll be passing in is this list of tokens, not a full sentence. So now for our list comprehension, it'll follow the same syntax as before, and we're just going to change the variable names. So now we're going to say, I want to return word for word in tokenized list if that word is not in stop word. Then we can assign this to text. So once again, this will just cycle through our list of tokens that we generated in the last lesson, check if each one is a stop word. If it is, then it'll toss it. And if it's not, then it'll keep it and return it to text in the form of a list. Now we want to tell this function to return text. Now we want to apply this to our data set. So we're just going to use a lambda function like we had before, and we'll store it in body text no stop. And we'll set that equal to body text tokenized. Then we'll apply our lambda function and call remove stop words on that X. So again, this will apply our function to each row in our data set on this column and store it in body text no stop. So let's go ahead and print out the first 5 rows of that. So you'll notice that the first row, the words Ben and for and the are now gone in our new list. And for instance, in the second one, you'll notice that in and are gone. So now we have a cleaned column that has been tokenized. We've removed the punctuation and we've removed the stop words. So that is a very abbreviated look at what a pre-processing pipeline looks like as you're preparing to get your raw text into a format that a machine learning model can actually use. In the next chapter, we'll explore some extra, slightly more advanced cleaning techniques and concepts that we can apply to our text to further help a machine learning model focus on the things that are really important. In the last chapter, we learned the basics of preparing our text to build a model. We learned how to remove punctuation, tokenize, and remove stop words to provide a clean list of words to Python. In this chapter, we're going to learn how to take our cleaning one step further to provide the model with better information for classifying the text. We'll introduce the concepts of stemming and lemmatizing in this chapter. Let's start with stemming. So what is stemming? The formal definition of stemming is the process of reducing inflected or derived words to their word stem or root. More simply put, the process of stemming means often crudely chopping off the end of a word to leave only the base. So this means taking words with various suffixes and condensing them under the same root word. Recall when we removed stop words, it was to reduce the number of words Python has to look at or consider. Stemming is shooting for the same goal by reducing variations of the same root word. If that doesn't make sense, let's jump into examples to see what it means in practice. So here's a collection of sets of 2 or 3 words. The words in each set have similar meaning. So stemming and stemmed are 2 distinctly different words, and Python will not inherently know that these are even related. What a stemmer will do is it'll reduce stemming and stemmed down to their base word of stem. So now, if stemming and stemmed are both represented by stem, we retain the semantic meaning of both words, and now Python views them as the same. Similarly, for electricity and electrical, they're pared down to electric. Berries and berry is interesting because it's more than just cutting off the end of it like we've seen previously. The stemmer will chop those both down to berry with an I. Lastly, connection, connected, and connective will all be chopped down to connect. So this seems pretty useful, but stemming uses very crude rules, so it isn't perfect. For instance, look at meaning and meanness. These words aren't really all that closely related, but they'll be both stripped down to a base of mean, and thus Python will think that meanness and meaning are the same exact thing. So stemmers are correct in most cases, but the trade-off with these simple rules is that it won't always be right. So this all seems interesting, but why do we really care about this? Why does this actually help us for model building? Well, if Python sees grew, grow, and growing as three separate things. That means it has to keep those three separate words in memory. Imagine every variation of every root word. Maybe we have 1,000 root words, but in our corpus, we have 2,000 total words with every suffix added to the root words. The alternative in this grow, grew, and growing example is applying the stemmer, and now it only has to know what grow means, as each variation of grow is replaced simply by grow. So Python has to look at a lot more tokens without a stemmer, and it doesn't know that these separate tokens are even related. So the benefits of a stemmer is it reduces the corpus of words the model is exposed to, so it's just grow instead of grew, grow, and growing, and it explicitly correlates words with similar meaning. So Python could learn through the training process that we'll discuss later that grow, grew, and growing are similar in meaning, but it also may not, depends on a lot of different factors. In this case, we're not leaving it up to Python. We're being explicit by replacing similar words with just one common root word. There are a number of different types of stemmers that use various algorithms and methods to generate the stemmed version of words. A few that are included in the NLTK package are the Porter stemmer, the Snowball stemmer, the Lancaster stemmer, and a regex-based stemmer. We'll be focusing this lesson on the most popular stemmer in this list, the Porter stemmer. We'll learn how to use the Porter stemmer in the next lesson. Now that we've learned what stemming means, we're going to put it to use. We'll do this in two stages. First, we'll test out the stemmer on specific words to understand how it works. Then we'll apply the stemmer on the SMS spam collection dataset to further clean up our data. So first we'll import the NLTK package, and then from that NLTK package, we'll call the Porter stemmer and store that as PS so that we can call it later. So let's go ahead and run that cell. Let's use the dir function to see what attributes and methods are contained within this Porter stemmer. So we'll run that, and there are a lot of different attributes and methods that you should explore, but this stem method is really the one that's used most commonly, and it's the one that we'll be focusing on here. Let's look at how the stemmer will handle a couple of examples. Let's try out this grows, growing, and grow example that we've been looking at. So we'll start with ps.stem, and then we just have to pass in the word that we want it to stem. So we'll start with grows, and we're going to copy this and paste it 2 more times, and then we just have to replace the word that we actually want it to stem. So we'll add growing for the second one, and then the last one we'll leave as just grow. Now, because we have 3 function calls in the same cell, Jupyter Notebooks will only print out the result of the last one, but we want it to print all of them out. So we have to explicitly tell it to print out each of these 3. So we'll add our print call for each of the 3, and then we can run it. So that reduces them all to the proper root word of grow. So now these 3 words can be treated as the same word rather than Python seeing them as 3 distinctly different words. So let's look at one more example. So we'll copy this code down, and we showed in the slides how the stemmer isn't perfect, where it stemmed both meaning and meanness down to mean, even though they don't represent the same thing. However, if you look at a different example that could be a little difficult, we'll do run, running, and runner. You could see how all 3 of these might be reduced down to just run, even though the first 2 are actions and the last one describes a person. So let's run it and see what the stemmer actually does. So the stemmer can actually tell that the first 2 are different than the last one in some way. So stemmers certainly aren't perfect, but they still do a pretty good job of identifying words that have the same meaning. All right, so now that we've learned a little bit about how the stemmer works on toy examples, let's apply it to the dataset we've been using in the SMS spam collection dataset. So let's start by importing the packages we need to read in the text and clean up our data. So we'll import pandas, the repackage, and then string. Then we'll also call the same option that we set in previous lessons to display more of the text message. And then we'll store our stop words as stop words for use when we clean up the data, and then we'll read in the data and assign column names in the same way that we have previously. Now let's just print out the first 5 rows, and you'll see just as we expected. And again, remember this is the raw text, this isn't the cleaned version. So now for the cleaning of the text. This function is exactly what we put together in the last chapter, but I just collapsed the three functions down into one. So we still have the same components. So we remove punctuation the same exact way, we tokenize it, and then we remove stop words. And then we use a lambda function to apply it to the data set. So let's just call the first 5 rows and let that run to make sure that prints out what we expect. So this is your tokenized list without any punctuation or stop words, just how we ended the previous chapter. Let's get into some new stuff. We saw that the ps.stem method is what stems each word. So the column that we'll be operating on from this data frame is this tokenized list. So we'll want to iterate through the list and stem each word and then return the stemmed version back to the list. So this should be starting to sound familiar at this point. We'll again write our own function using ps.stem within list comprehension in order to stem each word. So let's call our function stemming, and it'll accept a tokenized list of text. Now, if we recall with list comprehension, the way that we'll define it is word for word in tokenized text. And we'll assign that to text. So this will just return each word for each word in tokenized text. In other words, it'll take each word in this list and just output each word. So all we need to do to stem it is just say, instead of returning the original word that was in the list, apply the stemmer to that and return the stemmed word. So then that'll store all the stemmed words in a list called text, and then we'll just return text. And then lastly, just like we did before, we're going to use a lambda function to apply this to our data. And let's store it in a column called body text stemmed. And then we're going to run our lambda function on body text no stop. And then we want to apply the stemming function using this lambda function. So lambda x stemming x. So again, this will apply the stemming function to each row in our data frame. So we're going to run that and print out the first 5 rows. Now it's worth noting that the stemmer won't do a great job with slang or abbreviations, so it's probably not a great fit for a text message data set. I'll call your attention to a couple things. First, entry is changed to entry with an I, so it could also accommodate plural entries. Same thing with weekly. Another one is on the second line, lives is reduced down to live. So now you've learned what stemming represents and how to actually apply it. Stemming helps us reduce the corpus of words that the model is exposed to, and it explicitly correlates words with similar meaning. So in the next 2 lessons, you'll learn about lemmatizing, which is a different way to accomplish the same goal. In the previous lessons, we learned about stemming as a tool to reduce our corpus and correlate related words. In this lesson and the one to follow, we'll be learning about a related but slightly different tool called lemmatizing. So what is lemmatizing? The formal definition is that it's the process of grouping together the inflected forms of a word so they can be analyzed as a single term, identified by the words lemma. The lemma is the canonical form of a set of words. For instance, type, typed, and typing would all be forms of the same lemma. More simply put, lemmatizing is using vocabulary analysis of words to remove inflectional endings and return to the dictionary form of a word. So again, type, typed, and typing would all be simplified down to type because that's the root of the word. Each variation carries the same meaning, just with slightly different tense. So you might be thinking that this sounds an awful lot like stemming, and you wouldn't be wrong. They are aiming to accomplish the same thing, but they are doing it in just slightly different ways. And in practical terms, there's an accuracy and speed trade-off that you're making when you opt for one over the other. The goal of both is to condense derived words down into their base form, to reduce the corpus of words that the model is exposed to, and to explicitly correlate words with similar meaning. The difference is that stemming takes a more crude approach by just chopping off the ending of a word using heuristics without any understanding of the context in which a word is used. Because of that, stemming may or may not return an actual word in the dictionary. And it's usually less accurate, but the benefit is that it's faster because the rules are quite simple. Lemmatizing leverages more informed analysis to create groups of words with similar meaning based on the context around the word, part of speech, and other factors. Lemmatizers will always return a dictionary word. And because of the additional context that's considered, this is typically more accurate, but the downside is that it may be more computationally expensive. So this is a very brief introduction into lemmatizing. Instead of offering examples of how a lemmatizer works, I'm going to save that for the coding lesson next, as I want to illustrate some of the differences between how a stemmer handles certain words and how a lemmatizer will handle those same words. Now that we've learned what lemmatizing means, we're going to put it to use. So we'll do this in 2 steps. First, we're going to test out the lemmatizer on specific words to understand how it works, and then we'll apply it on the SMS spam collection dataset to further clean it up. So the same process that we saw in the stemming notebook. Just like we saw with stemmers, there are a few different lemmatizers as well that handle words in slightly different ways. So we're going to use the WordNet lemmatizer. This is probably the most popular lemmatizer. So WordNet is a collection of nouns, verbs, adjectives, and adverbs that are grouped together in sets of synonyms, each expressing a distinct concept. So this lemmatizer runs off of this corpus of synonyms. So given a word, it will track that word to its synonyms, and then the distinct concept that that group of words represents. So you can read more about it at the WordNet website right here. So we're going to import the NLTK package, and we'll call the WordNet lemmatizer from that package and store it as WN to be used later. We're also going to call the Porter stemmer again and store that as PS. This is so that we can test out how these 2 methods handle the same words differently. So let's run this cell, and then we'll call the dir function with the WordNet lemmatizer to see what attributes and methods are contained in here. So the one that I'm going to call out is the lemmatize function. This is the one that we'll be using in this lesson, and it's the most commonly used function from this tool. So let's add a cell, and when we looked at stemming, we mentioned in the slides that meanness and meaning were both condensed down to mean. So Python would now assume that meaning and meanness were exactly the same, which is inaccurate. So let's confirm that by printing out the stem from the Porter stemmer, so ps.stem for meanness, and then we'll just copy that down to the second line, and we'll print out meaning. So again, we need the print statements because Jupyter Notebooks will only return the most recent function call. So run that, and it returns mean for both of them. Now let's explore how the lemmatizer might handle these differently. So we'll have to do print again, and this time call the WordNet lemmatizer dot lemmatize meanness for the first one, and then we'll just copy that down to the second line, and we'll replace meanness with meaning. Run that. Also note that this takes a little bit longer than the stemmer. Again, that goes back to because it's not just using a set of simple rules to chop off the suffixes, it's actually tracking it against the synonyms to find what group these fit into. You'll notice that both of these were untouched. So this brings us to an important point, and I'd like to highlight 2 things. First, stemming uses the algorithmic approach, so it's only concerned with the string that it's given, and it'll essentially chop off the suffix. Lemmatizing is a little bit more complex in that it searches the corpus to find related words and condense it down to the core concept. The problem is that if this word isn't in the corpus, then it'll just return the original word. So that's what's happening here. So with that said, not condensing it in this case is probably better than incorrectly stemming it using the Porter stemmer. So that's one example. Let's look at one more example. So let's add another cell, and we're going to copy the stemming down here, and this time we're going to try goose versus geese. These are clearly related. One is just the plural of the other. So let's just run the stemmer on that, and you'll see that the stemmer doesn't quite know what to do here with goose and geese, so it returns 2 different root words. So again, Python will still view goose and geese as 2 different things, even if you use the stemmer. So let's try to use the lemmatizer on goose and geese and see if the lemmatizer is any better at handling these differences. So you'll see that the lemmatizer correctly maps both of these back to goose. Python will be able to now realize that these are the same words. So lemmatizer can be quite powerful in some relatively complex situations. So now that we've learned a little bit about how the lemmatizer works, we're going to do the same thing that we did with the stemmer, where we're going to read in our SMS spam collection data set, clean it up by tokenizing, removing punctuation stop words, and then we'll apply the WordNet lematizer at the end. So now reading in our SMS spam collection data set in the same way that we have the last few lessons and assigning the column names. Let's just print out the first 5 rows just to make sure it's reading in as we expected, and it is. And then just as we saw with the stemming lesson, we're defining our clean text function where we have separate lines for the punctuation, the tokenizing, and removing stop words that we just took from last chapter. And then we apply it to our data set using a lambda function. And again, we'll just print out the first 5 rows just to make sure that it's doing what we expected. And it's removing our tokenized list without stop words or punctuation. So let's jump into the lemmatizing portion of this. We saw before that wn.lemmatize is what applies the lemmatizer for each word. The field that we'll be working with is a list of words in body, text, no stop. And so we're going to do exactly what we did in the stemming lesson by using list comprehension to iterate through the list of tokens and then return the lemmatized version. So let's define our function that we'll call lemmatizing, and I'll expect to be passed in a tokenized list of text. And then we'll define our list comprehension in the same way that we have in the last few lessons. So word for word in tokenized text. And again, we'll assign this to text. Just like we did in the stemming exercise, we'll just apply our lemmatizer here so that it returns the lemmatized version of the word instead of the original word. And then we'll tell this function to return that text. And lastly, we'll use a lambda function to clean our data set. So we'll tell it that we want to store the cleaned up version in body text lemmatized. And then we want to apply this on body text no stop. And we'll apply this using a lambda function, lambda x, lemmatizing x. And then let's go ahead and print out the first 10 rows. So we have this new cleaned up column, and I'll call your attention to a couple of things. Just like the stemmer, the lemmatizer won't do particularly well with slang or abbreviations. So it's not ideal for this data set. It might be much more effective if it was used on a collection of book reports or journal articles. So I will call your attention to a couple things that the lemmatizer was able to impact. So it transitioned this lives down into life, and it also transitioned mobiles into mobile. And so you'll notice that these aren't super interesting examples necessarily, but as you saw above, the lemmatizer can do some relatively sophisticated things, at least more sophisticated than the stemmer. So now you've learned what lemmatizing is and how to actually apply it. So both stemming and lemmatizing helps us reduce the corpus of words that the model's exposed to, and it explicitly correlates words with similar meaning. The lemmatizer is typically more accurate than the stemmer, but the trade-off is that it takes a little bit longer to run. So based on your machine learning pipeline, if the lemmatizer is going to be a bottleneck, then you may opt for the more simple stemmer. So these lessons were very much geared towards just introducing you to the tools and learning the extreme basics to apply it. I encourage you to dig in further to learn more about these tools. Up to this point, we've discussed several times how Python really only sees a string of characters when it looks at text data. So now that we've learned how to clean up that text data that we'll be using to build a machine learning model, now we have to learn how to get that text into a form that a machine learning model and Python can actually use to understand and train a model. The process that we use to convert text to a form that Python and a machine learning model can understand is called vectorizing. This is defined as the process of encoding text as integers to create feature vectors. Now, if you don't have much machine learning experience, you may be wondering what a feature vector is. A feature vector is an n-dimensional vector of numerical features that represent some object. So in our context, that means we'll be taking an individual text message and converting it to a numeric vector that represents that text message. How exactly we do that is what we're going to dig into in this chapter. So what does that mean within the context of the problem that we're working on? We're going to revisit a slide that we used in chapter 1. So we start with raw text, and then we tokenized and clean the text, just like we saw in last chapter. Then we get to the vectorization step, and basically what we're doing when we vectorize text is we're taking this data set that has one line per document, with the cell entry as the actual text message, and then we're converting it to a matrix that still has one line per document, but then you have every word used across all documents as the columns of your matrix. And then within each cell is counting how many times that certain word appeared in that document. And this is called your document term matrix. We'll be referring to this term quite a bit. Then once we have this numeric representation of each text message, then we can carry on down the pipeline and fit and train a model. If this doesn't quite make sense yet, that's okay. We're going to look at a general example in the next slide and then a number of more specific examples as we move through the rest of this chapter. But it is important to understand the motivation behind this process. So as we mentioned previously, that when looking at a word, Python only sees characters. So we need to convert this into a format that Python can understand in order for our machine learning models to start to learn what certain words indicate about the overall sentence or document or label that we're trying to predict. So we vectorize this text to create a matrix that only has numeric entries. So in our case, counting how many times each word appears in each text message. The machine learning algorithm understands these counts. So if it sees a 1 or a 2 or a 3 in a cell, then that model can start to correlate that with whatever we're trying to predict. In our case, that's spam. To roughly understand then what the words, sentences, and documents represent. So in our context, this means it can use how frequently these certain words appear to determine whether the individual text message is spam or not. Okay, enough talking about the concepts. Let's look at what this actually means. Going back to our spam ham dataset, let's look at this extremely simplistic example where we only have 15 text messages and we want to classify them each as either spam or ham. Let's just say there are 400 unique words across those 15 text messages. That would mean our matrix after vectorizing would still have 15 rows, just like this one does, one per text message, and it would have 400 columns, one for each unique word. And each cell entry would count the number of times that word was used in each text message. Again, this is called your document term matrix. This matrix I'm showing here is a subset of your full document term matrix. We're just focusing on two words here used in text messages, offer and LOL, along with the label of either spam or ham. But again, in reality, this ... here would represent the other 398 words that were used across these text messages. So that's what this looks like after vectorizing. Now, how does a machine learning model use this information to learn what these words mean? I mentioned before that by looking at the counts in the cells that it can start to correlate which words happen in combination with certain labels. So let's isolate just the non-spam messages here. You can start to notice that offer occurs very infrequently, but LOL occurs in a lot of these non-spam text messages. So in the first message, offer occurs 0 times, LOL occurs once, and you can imagine that that would also occur with many other words that we're not showing here. In the second text message, neither occur. And then in the fifth, offer doesn't occur at all, LOL occurs 4 times, and so on. So from the numbers here, the model could pretty easily pick up on the fact that LOL occurs quite frequently with non-spam text messages, and offer occurs very infrequently. You could see how this would allow a model to start to learn how to predict when a text is spam or not, based just on the text body. So now let's do the same thing, but we'll jump over to the spam messages. You can pretty quickly notice that it's the opposite. Offer occurs quite frequently, while LOL occurs quite infrequently. So the model would pick up on the fact that offer occurs quite frequently in spam messages, and LOL occurs quite infrequently. So now, only considering these two words, the model has learned that offer occurs frequently with spam and infrequently with non-spam, while LOL occurs frequently with non-spam and infrequently with spam. So you could see how maybe with even just these two words, the model could start making ham or spam predictions about new text messages based only on the number of times these two words occur. With that said, this is an extremely simple and exaggerated example for the purpose of illustration. In reality, the model would need to learn the relationships of much more than two words to make it an accurate prediction. But this example was meant to show how vectorizing helps the model roughly learn what words correlate with which labels. So far, I've entirely been talking about the entry of each cell in the document term matrix containing the count of how many times a given word appears in that text message. But that's only one method of vectorization, and that's called, not surprisingly, count vectorization. There are two other variations of count vectorization called n-grams and term frequency inverse document frequency, which is often referred to as TF-IDF. We're going to cover each of these three methods of vectorization in more detail in the next 3 lessons. Now that we've learned a little bit about what vectorization is and why it's necessary, we're going to jump into learning how to actually implement 3 different types of vectorizers over the next 3 lessons. Keep in mind that all 3 of these methods will generate very similar document term matrices, where there's one line per document, or text message in our case, and then the columns will represent each word, or potentially a combination of words, as we'll see in the next lesson. The main difference between the 3 is what's in the actual cells of the matrix. So we'll start with count vectorization. This is basically the example that we ran through at the end of the last lesson. So count vectorization creates the document term matrix and then simply counts the number of times each word appears in that given document, or text message in our case, and that's what's stored in the given cell. So it's pretty straightforward. So again, we're going to use our SMS spam collection data set, and then we'll build a function to clean it up just like we've done in the last few lessons. So in order to do this, remember to import pandas, string, and NLTK. Now, we're reading in stop words just like we had before, and I'll just call out that I opted to use the Porter stemmer to truncate the words. You could use the lematizer or experiment with a different stemmer. I opted to use the Porter stemmer just because it's a little bit faster than the lematizer. So we can go ahead and run this, and then we have the same condensed cleaning function that we used in the last chapter to remove punctuation, tokenize, and then remove stop words. The only change that I've made is now I'm stemming each word that is not in the stop words. So what this will return is a cleaned and stemmed list of tokens. Now, the difference is we're not going to use a lambda function to apply it to our data like we have in the past. The count vectorizer actually allows you to pass in a function to clean and tokenize your data. So you'll see as we move forward, we'll just pass in this clean text function, and let's go ahead and run that. It'll do the cleaning, the tokenization, and the vectorization all in one step. So the first thing that we need to do to implement the count vectorizer is to actually import it. So that's stored in sklearn feature extraction text. So we'll say from sklearn feature extraction text, import count vectorizer. For sklearn objects, the first thing we always need to do is instantiate that object and define our parameters. So we're going to store it in count vect, and we'll call the count vectorizer. And then as part of count vectorizer, there's an analyzer parameter, which will allow us to pass in the function that we created to clean up the text. And it'll apply that function all at the same time that's vectorizing the text. So we'll say analyzer equals, and we just pass in the name of our function, which is clean text. Feel free to explore the other hyperparameters for count vectorizer in the sklearn documentation. By not calling any of the other hyperparameters like we are here, they'll just remain set at the default, which is okay for this example. Now we want to use that count vect object, and we want to fit it on our body text. So we'll call data body text, and then we'll store that as x counts. Now there's one catch here. If we only fit it, it won't actually do anything to our data. It'll just train the vectorizer object to learn what words are in the corpus. So if we want to actually fit it and then transform our data, in other words, if we want to fit the vectorizer and then actually vectorize our data and turn them into feature vectors, then we'll need to call fit underscore transform, and that'll actually do the fitting and transform our data. So what will be stored in x counts is the vectorized version of the data. Now this concept of fitting and then transforming, or fitting and predicting, will become much more clear as we use it quite extensively over the next few lessons. Now that we have our actual counts, let's go ahead and print out x counts shape to see how many text messages we have, and then how many unique words we have, which will represent how many columns we have. And then also let's print out from count vect, which is our stored vectorizer, we can call this get feature names method. And what that'll do is it'll print out all of the unique words that are found across all of the text messages. Okay, so now we can just run this. It'll take a second to run, and it'll print out the shape at the very top. So this tells us that there are 5,567 text messages, and across those 5,567 text messages, there are 8,104 unique words, which means our document term matrix has 5,567 rows and 8,104 columns. And then the get feature names basically means here are the names of the columns of our document term matrix. So you'll see a lot of these feature names are actually numbers. So we could have created a process to remove these numbers, but for this simple example, we didn't do that. This shows you how to actually fit and transform your data set, but to get a better feel for what your data set actually looks like once it's vectorized, I'm going to take a much smaller sample because it's a little difficult to really visualize a matrix of almost 6,000 by 8,000. Okay, so the first thing we'll do is just select the first 20 rows or the first 20 text messages from the original data set. Then we're going to run through the exact same process that we created before. We'll call our count vectorizer, and for our analyzer, we'll pass in our cleaning function. We previously stored this as countVect. This time we'll just call it countVectSample. And then now, if you remember, now that we've instantiated that object, now we can use that countVectSample, and we do fit transform, and we'll call it on data sample that we've just created on the body text column. And then we want to go ahead and assign this to xCounts sample. And then just like last time, we'll go ahead and print out the shape, x_counts_sample.shape to print out the number of rows and columns of our new data set, and then print out the feature names. countVectSample.get feature names. So now we can go ahead and run that, and you can see this is much more digestible than we saw before. So now, instead of 5,567 by 8,104, our matrix is just 20 rows by 192 columns. And here are the new feature names. So there's some numbers in there, but you can also see around, brother, call, caller, things like that. One thing that I want to note is that the raw data output of the count vectorizer is what's called a sparse matrix. So what is a sparse matrix? Well, when you have a matrix in which a very high percent of the entries are zero, as we do in this case, and you'll see that in just a minute, instead of storing all these zeros in the full matrix, which would make it extremely inefficient, it'll just be converted to only storing the locations and the values of the non-zero elements, which is much more efficient for storage. So if we just try and print out this xCounts sample, you would have previously expected it just to give us our matrix, but instead it'll just say this is a sparse matrix object with 218 stored elements. So in order to print out the matrix, we have to expand this sparse matrix out to a collection of arrays and then create a data frame from that. So we'll start with xCounts sample, and then to expand them all out to arrays, we just add this toArray method. And so now for each row, instead of storing just the non-zero elements, it adds those zeros back in there. So now we have a full array that is 192 entries long. Lastly, to create a data frame out of this, we just have to call pd.dataframe and wrap that around xCountsSample.toArray. And then we can store that as xCountsDF for data frame. And then let's go ahead and print that out to see what it looks like. And this is our document term matrix. So you'll see it's 192 columns by 20 rows. And you'll see the counts in here, which are mostly ones in the columns that you can see here. There are 2s, 3s, 4s scattered throughout as well. You'll notice that the column names don't contain the word they actually represent. They're just numbered from 0 to 191. Now again, for Python, this doesn't really matter because it doesn't know the difference between a column name of 5 and a column name of text. So it's just going to learn from the entries in that column and its relationship with our label to figure out how it can contribute to the model. Now, with that said, it would be nice for our purposes to be able to see what words those columns actually represent. So we can do that by calling this getFeatureNames method. So count vect sample.get feature names like we called above. And then all we have to do is just assign that to the column names of our data frame. So xcountsdf.columns. So that'll just pull all the feature names that we looked at before and store them as the column names of this data frame that we just created. So let's go ahead and print out that data frame. And now you'll see this is exactly the same data frame. Now we just have the actual column names here. So you'll notice, for instance, for the very first text message, the numbers like 1, 100, and then wet and winter and word don't occur there. So for instance, in the first text, you'll see that win and weekly do occur, while numbers like 11 and 12 do not. And you can carry that through the rest of the text messages. So that's a brief introduction into the count vectorizer. Now that we've established some of these basics and we understand how to call it in sklearn, it'll be much easier to run through the next two lessons. This lesson is going to look very similar to the last lesson, as we're going to follow almost exactly the same code template. But this time we're going to do it with n-grams instead of the count vectorizer. So the first question, what are n-grams? The n-grams process creates a document term matrix like we saw before. Now we still have one row per text message, and we still have counts that occupy the individual cells, but instead of the columns representing single terms, like we saw in the last lesson, now they represent all combinations of adjacent words of length n in your text. So as an example, let's use the string NLP as an interesting topic. Hopefully you agree. This table shows how that would break down. In n-grams, if n equals 2, then that's called a bigram, and it will pull all combinations of 2 adjacent words in our string. So in NLP is an interesting topic, it will pull out 4 tokens. NLP is an interesting topic. When n equals 3, that's called trigrams. It'll pull all combinations of 3 adjacent words in our string. So it will create 3 tokens. NLP is an interesting, and an interesting topic. So again, when n equals 4, that's called a 4gram, and it'll pull all combinations of 4 adjacent words in our string, as you see here with these 2 tokens. So you can make n as large or as small as you'd like, and you could think of count vectorization as n-grams with n equal to 2, so it'll just pull out the unigrams. When you use n-grams, there's usually an optimal n value or range that will yield the best performance, so generally you'll tune this value to see what generates the best model. The value here is that you get a little more context around your words. Rather than only seeing one word at a time, you'll see 2 or 3 or 4. Just to tie this back to something that we talked about earlier, NLP in everyday life, Google's autocomplete uses an n-grams-like approach. So if you type natural language into Google, it knows that a very regularly used trigram starting with natural language is natural language processing. So it might suggest that as a full phrase that you'd like to search for. So let's jump into the code. And again, we're going to use the same template as last time. So we'll move pretty quickly through some of these cells. So this step, again, is just to read in the data, and it's exactly like the last notebook, along with instantiating the Porter stemmer and storing our stop words. So let's go ahead and run that. Now, on the cleaning, this is a little bit different. We have to make a slight alteration to what we were doing previously. If you remember with the count vectorizer, we had this clean text function that we have here, and it returned a tokenized list directly into the count vectorizer function. So it did it all at once, so it was handling that cleaning and tokenizing for us. With n-grams, it wants a string passed into it, so that it can look for the adjacent words in the string and chunk them together, rather than taking an already tokenized list. So all I did was add this join function in the very last step where it takes the tokenized list, checks for stop words, and then returns the stemmed version of those stop words. If you recall earlier when we removed punctuation, we had to add back this join function so that it would take each individual character and join them back together. We're doing exactly the same thing here in this last step, except now instead of joining individual characters, we're just joining tokens back together. and adding the space back in between them to create a sentence. So that's the only change I made, is taking this tokenized list that we were outputting before and just restructuring it back into a string. So we're going to pass this clean text function into a Lambda function and create a new column called clean text. So this is nearly the same as what we've been doing in the past. But now we just took the tokenized list and created the string out of it. So now when we run this cell, now you can see this clean text column has all the tokens from our tokenized list. It's just reconstructed back into a sentence. Jumping into the n-grams portion. N-grams will still use the count vectorizer because it's still counting the occurrences of these groups of words. So just like before, we'll call from sklearn.featureExtraction.text import count vectorizer. The first thing, if you recall, that we have to do is instantiate the count vectorizer. We're not going to use this analyzer parameter that we saw in the last section because we're not passing our cleaning function into this. We already have the final column that we need to pass directly into the count vectorizer, so we don't need that analyzer parameter to be set to anything. What we do need is we need to tell it that we're interested in n-grams. So the default for count vectorizer is for n-gram range equal to 1, 1. And what that tells the count vectorizer is we only care about unigrams. Now, if we change the second number there to 2, then it'll tell it we want to search for unigrams and bigrams. Now, if we change that second number from 2 to 3, then that tells the count vectorizer that we want to search for unigrams, bigrams, and trigrams. So again, this parameter is telling the count vectorizer the range of n-grams that we'd like to look for. For this exercise, we're only going to look for bigrams, so that'll just be 2, 2. We're instantiating this count vectorizer, and we can store it as n-gram_vect. Now, if you recall from the last lesson, what we want to do is call this n-gram_vect, and we're going to do fit_transform in order to fit and then transform our data. We're going to run it on the cleaned text column that we created just up above, and we'll store that as x counts. And then, just like we did in the last lesson, we're going to go ahead and print out the shape of x counts, and then we'll print out the feature names using this get feature names method that we used in the last lesson. So if we run that, now you can see that we still have the same 5,567 rows, but now instead of the 8,000 that we saw before, you can see that there's over 31,000 columns. So that means 31,000 unique combinations of 2 words. Now in these feature names, you'll see 2-word combinations. So you'll have 150 space ppm. Let's get beyond the numbers. So you see age, gender, age how, age join. So that's just an example of the kind of features that we'd be looking at here. So now, just like the last time, we're going to jump to a smaller sample so we can actually visualize what we're looking at here. So we'll start with the sample of the first 20 text messages, and then we're going to go ahead and just copy our code down here, and we'll just change the names that we're using. So for count vectorizer, we'll still use n-gram range of 2 to 2. Now let's just change what we're storing it as to n-gram_vect sample. And then again, we need to call that in the second line. So now we want to fit and transform using that new count vectorizer. And then the data frame that we want to call is not the original data frame, but data sample. And we'll store this as x counts sample. And then we want to print out that shape. And lastly, we can just grab our vectorizer and we'll get the feature names from our new vectorizer. So let's go ahead and run that one. Now, instead of over 31,000 columns, now we're back down to 198. But if you remember, that's still higher than the 192 unigrams that we saw in our last notebook. At this point, it's worth noting that using this n-gram range can end up creating a matrix with a ton of features. So if you did an n-gram range of 1, 2, so that's grabbing all the unigrams and bigrams. In our last lesson, we saw that there were over 8,000 unigrams in the full data set. And in this lesson, we saw that there are 31,000 bigrams in the full sample. So together, that's 39,000 columns that are only using unigrams and bigrams. Now imagine if we added trigrams on top of that. So just be careful with the n-grams. It's definitely worth experimenting to see both what's going to work within memory and which is going to help you generate the best model. Just like we did last time, we know the raw output is a sparse matrix, so we're going to convert it to a data frame and add the proper column headings. So again, we'll take this x counts sample, and just like last time, we need to create an array from each entry, and then we'll wrap that in pd.dataframe so that now it takes all these arrays and creates a data frame out of it. And then lastly, we'll store that as x_counts_df. And then if we want the column names, we can do the same thing that we did in the last lesson, where we'll say x_counts_df.columns. And then we want to assign the column names based on our n-gram vect sample vectorizer. And we'll call the get feature names method. And then we'll just go ahead and print out x_counts_df. So this tells us that 2005 text and 21st May occur in the very first text message, but not in any of the other text messages. And then, for instance, way meet, right here, occurs in the very last text message, but not any of the other ones. This is a brief introduction to how you implement n-grams. The value to n-grams over regular count vectorization is that it provides a little bit more context around words. And there is certainly a trade-off when you're choosing your n value for your n-grams. If you select only bigrams, then maybe that's not enough to provide useful context. But if you go all the way up to 7 grams, you're going to have a ton of features, and you'll only see the same 7 gram, in other words, the same sequence of 7 words, maybe in one text message. So in other words, what that means is every column of 7 grams would be non-zero in only one row, and you'd have a massive matrix. So n-grams can be powerful, but they require a little bit more care in implementing. So we've gone over the count vectorizer and n-grams. Now we're going to touch on the last vectorization method that we'll be covering, term frequency inverse document frequency, often referred to as TF-IDF. These aren't the only 3 methods of vectorizing, but they're the only 3 that we're going to cover here because they are the most popular. So what is TF-IDF? TF-IDF creates a document term matrix where there's still one row per text message and the columns still represent single unique terms, but instead of the cells representing the count, the cells represent a weighting that's meant to identify how important a word is to an individual text message. So this formula lays out how this weighting is determined. It may look a little bit intimidating, but it's actually quite simple. You start with this TF term, which is just the number of times that term I occurs in text message J, divided by the number of terms in text message J. So it's just the percent of terms in this given text message that are this specific word. So for instance, if we use I like NLP and the word we're focused on is NLP, then this term would be 1 divided by 3, or 0.33. Then the second part of this equation measures how frequently this word occurs across all other text messages. So it calculates the number of text messages in the dataset divided by the number of text messages that this word appears in, and then it takes the log of all of that. Let's just say that we have 20 text messages, so that's going to represent n in this case, and only one of those contains NLP, so that's going to be df. So the second part of this equation would then be log of 20 divided by 1. So as this fraction inside the log gets larger, the log of that fraction also gets larger. So now let's say that you have 40 text messages instead of 20, but NLP still only occurs in one of them, so the denominator here will still only be 1. So now this fraction is 40 over 1. The term NLP is less frequent, and this term collectively is going to be larger. So basically, all this says is that the rarer the word is, the higher that this value is going to be. If a word occurs very frequently within a particular text message, so that's TF, but very infrequently elsewhere, that's going to be the second term, then a very large number will be assigned, and it'll be assumed to be very important to differentiating that text message from others. In summary, this method helps you pull out important but seldom used words. Enough on definitions, let's jump into the code. So you should be getting really good at this by now. We're going to use the same template as the last two lessons. Again, we're reading in the data the exact same way that we did the last couple lessons. We're instantiating the Porter stemmer and storing our stop words. And we'll go ahead and run that. And then we can go down to our clean text function. So for this cleaning, we're going to jump back to how we treat it for the count vectorizer. Remember, with ngrams, we deviated a little bit from this process because that vectorizer needed a full sentence passed in instead of a tokenized list. But for the TF-IDF vectorizer, we can go directly back to passing in the tokenized list. So we'll define this function, and then we can pass that directly to the vectorizer, just like we did for the count vectorizer, and it'll handle the cleaning, tokenizing, and vectorizing all in one step. So let's go ahead and run this clean text function. Now let's get into actually reading in the TF-IDF vectorizer. So just like the count vectorizer, it's stored in sklearn feature extraction.text. So we'll say from that import TF-IDF vectorizer. Now, in the same way that we did previously with each of the other vectorizers, we first need to instantiate it. So we'll call TF-IDF vectorizer, and then we're going to use this analyzer parameter, and we're going to pass it in the name of our cleaning function. And then we can store this all as TF-IDF vect. Now that we have that stored, we can call the TF-IDF vect and use the fit transform function and run that on data bracket body text column. And then we're going to store that vectorized data in X TF-IDF. Now, just as we did before, we can go ahead and print out the X TF-IDF shape. And we'll print out the feature names from TF-IDF vect. So you go ahead and run that. You'll notice that the shape is exactly the same as it was for the count vectorizer. 5,567 rows by 8,104 columns. Now that is expected because, as we talked about in the opening, the columns are still represented by unique words. The only difference between the TF-IDF vectorizer and the count vectorizer is what's in the actual cells, not the shape of the matrix itself. Now, let's take a smaller sample so we can dive into that and better visualize what's going on here. So we're going to pull the first 20 rows of data and store them in data sample. So I'll grab the first 20 text messages. And then we can just grab this code up here, and we can basically just copy it down. And we can just change the name of our vectorizer, our vectorized data, and the data that we're running it on. So we'll change TF-IDF vect to TF-IDF vect sample. Then this is called 2 more times in the fit transform, and then get feature names. Then we'll change X TF-IDF to X TF-IDF sample. And then again, we'll call that for the shape. And lastly, we want to run this all on data sample, not the raw data. Okay, so this looks as expected, similar to what we saw before. 20 rows, 192 columns, the same as we saw when we did this for the count vectorizer. And the feature names are as expected. So now let's create a data frame from the sparse matrix and add in the column names so we can look at what this full data set actually looks like. Again, we're going to take this X TF-IDF sample that we created just above, and we're going to call this to array to change it from a sparse matrix into an array. And then lastly, we'll wrap this in pd.dataframe to create a data frame out of all those arrays, and we'll store that as X TF-IDF df. Now, if you recall before, we can assign the column names by just saying TF-IDF df.columns, and then call the TF-IDF vect sample vectorizer and call get feature names. And then let's go ahead and print out XTF-IDF df. You'll notice this looks a lot different than our other matrices. Instead of regular integers in these cells, you have decimals. This 0.2316 is likely more important than this 0.1977. So this 0.2316 is likely more important than this 0.1976. Now what that means is either 12 occurs more frequently in the 5th text message than 11 does in the sixth text message, or it means 12 occurs less frequently across all the other text messages than 11 does across all the other text messages. So in summary, we kind of created this false choice here, indicating that there are three different ways to vectorize. These are all very closely related though, and some can actually be used together. So TF-IDF is basically count vectorizer that includes some consideration for the length of the document and also how common the word is across other text messages. And then ngrams is just used within either of these two methods to look for groups of adjacent words instead of just looking for single terms. So they're all just slight modifications of each other, and typically you'll test different vectorization methods depending on your problem, and then you let the results determine which one you use. So that wraps up our vectorization section. Next, we're going to learn about feature engineering. So let's recap quickly. Up to this point, we've learned how to read in messy raw text, how to clean data by removing punctuation, removing stop words, stemming, and lemmatizing, and how to vectorize our data a few different ways to get it into a format that a model can use. So we have some clean data with labels that are prepared to be used for some modeling. Now there is only one step between us and building the actual model, and that's feature engineering. It's worth noting that this section could be an entire class on its own, so this is a very, very brief summarization of the topic. First, what is feature engineering? Feature engineering is the process of creating new features and or transforming existing features to get the most out of your data. So up to this point, we've just been talking about what we were given without really imagining what other features we might be able to extract from this data that would be helpful to predict spam or ham. The absence of this step could mean we're potentially leaving some significant value on the table. So the model will now see the words in the text as represented by the vectorization, but nothing else. What else could we extract from that text that would be helpful for the model to decipher spam from ham? For instance, maybe we could include the length of the text field. Maybe spam tends to be a little bit longer than real text messages, or maybe we could include what percent of the characters in the text message are punctuation. Maybe real text messages underuse punctuation. Or maybe what percent of characters are capitalized are indicative of whether it's spam or not. So that's a couple ideas of some features that you could create that would help our model identify spam from non-spam. So given these new features, or really any other already existing features, maybe you need to apply some sort of transformation to your data to make it more well-behaved. One broad popular type of transformations are called power transformations. So this would include squaring your data, taking the square root, etc. We'll dig more into that in the next couple lessons. One example of why you might need to transform your data would be if you have a very skewed data set with a very long right tail where you have a lot of outliers. In that case, you might want to apply a log transformation, which basically pulls that long tail and all those outliers back towards the bulk of the data. And what this does is it helps the model draw correlations and better understand the data without trying to overfit to that long tail and those outliers. Another topic that falls under transformations is standardizing your data, or transforming it all to be on the same scale. Some models perform better when all features are on the same scale. It's especially important as you get to this phase that you're keeping the problem context in mind. When you do feature creation, you're always trying to imagine what additional information might be helpful to the model within the context and understanding of what exactly it's trying to predict. For instance, as an extreme example in our spam detection problem, the number of A's that appear in a text message likely isn't predictive of whether this is spam or ham, but maybe the amount of punctuation or the length of a text message is. So always keep your problem in mind, and this is a stage where you're allowed to get a little bit creative to try to extract as much value out of your data as possible. We're going to dive into feature engineering, and we'll start by creating two new features. Again, we do this to try to extract as much value out of the given data as we can by imagining what additional information would be helpful for the model to make accurate predictions. As I mentioned in the last lesson, this is a large enough component that it could really be its own course. So we're really only going to touch on very high-level concepts, just so we can get a basic working prototype. So first, we're going to read in the data in the same way that we have before, you'll notice that we're not reading in the stemmer or stop words like we have the last few lessons. We're going to build these new features on the raw, unclean text, and you'll see why in just a minute. I'm going to go ahead and run this cell, and then we'll start creating our first feature. So the first feature we're going to create is a text message length feature. We're going to work under the hypothesis that spam messages tend to be longer than real text messages. So we'll create this feature, and then we'll explore whether our hypothesis is accurate. This is the easier of the two features that we're going to create. So we're just going to use a lambda function that you should be pretty comfortable using at this point. So the way that we're going to do this is we're going to call data and call the body text column from that data frame, and then apply our lambda function. And all we need to do is just apply len x, and they'll just get the length of each of the text messages. However, there is one catch here. The length will also count white space. So if you have a text message that's 10 characters long with 9 white spaces, that's different than one with 10 characters and 0 white spaces. So there's an easy fix for that. All we have to do is subtract out x.count, and then we tell it what to count, and we say just count white space. So this will take the length of x and subtract out the number of white spaces, so it'll give you the number of characters in the text message. And then lastly, we just want to assign this to a new feature that we'll call body len. Close that out. And then we'll just print out the first 5 rows. You can count the characters if you really want to. I can confirm this function is properly counting all non-white space characters. So for our next feature, we're going to generate the percent of each text message that is punctuation. Again, we're going to work under the hypothesis that real text messages use less punctuation than spam. And again, we can explore that hypothesis in just a couple minutes. To circle back, this is why we're using the raw text and not the clean text, because the clean text has no punctuation. So we're going to import our string function, and then we're going to create a function to generate this value, and then we'll apply it using a lambda function. We'll import string, and then let's define the function, and we'll call it count_punct, and we'll accept some text. Now, this is going to work on list comprehension like we used before. So this list comprehension will be spelled out like this. We'll say 1 for char in text if char in string dot punctuation. And then we'll assign that back to count. And so now what this does, if you recall what we did when we removed punctuation, is what we said is char return the character for each character in text as long as that character is not in string dot punctuation. Now we're just flipping it. And so what we're doing is we're cycling through each character, seeing if it is punctuation. And then instead of returning that character, we're just returning a 1. So this will just return a 1 every time it finds punctuation in a given text message. So now instead of a list of 1s, what we really want to do is sum up all of those 1s. So if we just wrap this list comprehension in sum, it'll now just count the number of 1s that's returned. Now that we have that count, we can go ahead and return this count. But we don't actually want to return the count. We don't want the amount of punctuation found. We want to return the percent of the text message that is punctuation. So we can take this count and we're just going to divide it by the length of the text message, or the number of characters in the text message, which we created in the feature above. So let's just pull that down. But the one catch is we don't want to say length of x because this function doesn't know what x is. To this function, x is text. We'll say take the length of the text message passed in and subtract the number of spaces that you find in that text message. So now we'll just replace the x's with text. So now we have len text minus text.count, where it's counting the number of spaces. Since this is decimal, let's just tell it how many places to round that decimal to keep it clean. We'll tell it to round it to 3 decimal places. Okay, now that we've rounded to 3 decimal places, let's just make our lives a little easier and multiply it by 100. So now instead of getting a decimal, we're actually getting a percentage. So instead of 0.05, now it'll print out as 5, and we'll know it's 5%. And lastly, now we need to apply this using a lambda function. So we'll call data body text, and then apply lambda x count punct x. And then we need to assign that to a new column that we'll call puncts %, close our bracket, and then let's just print out the first 5 rows. The first text message is 4.7% punctuation, the second one's 4.1%, and so on. There are a number of other features that we could have created, for instance, the number of the characters that are capitalized. But we're going to skip that and we're going to jump into quickly evaluating what these new features look like. So again, the goal here is to generate new features that help a model distinguish spam from real text messages. So it's always useful to find some way to see if your new features appear to be predictive or correlated to the response in some way. So in the next video, we'll go ahead and create overlaid histograms in order to see the value of these new created features. We're going to pick up right where we left off last lesson. So if you're just joining us, go ahead and run all the previous cells in this exercise notebook. Now that we've created 2 new features, we want to evaluate those features to see if they might be providing any new value to the model for distinguishing spam from non-spam. As I mentioned at the end of the previous lesson, we'll use overlaid histograms to look at the value of these created features. So we're going to import pyplot from matplotlib, and we're going to import numpy and store it as np. And then we're going to tell Python to print out matplotlib inline right in our notebook. So the function call to build these histograms is pyplot.hist. So basically we're going to build 2 histograms. The first is going to look at the distribution of our body length for spam, and then the second one is going to look at the distribution of body length for non-spam. And that's how we're going to use these histograms to see if this new created feature is helpful for distinguishing spam from non-spam. So the first parameter that we have to pass in is the thing that we actually want to plot. So that's body len. But what we actually want to do for this first one is we want to filter that data frame to only include rows where the label is spam. So we do that by saying data bracket label equal spam. So it'll filter that data frame down to rows that are only spam, and then it'll look at the body length column for those rows. The next thing we have to pass in is the bins for our histogram. We're going to define that in our own way. So the way that we'll do that is we'll use numpy's linspace function. And what we're going to pass in is the starting point, which is going to be 0, and then the maximum. And for our case, for body length, we'll say it won't go any higher than 200. Then we tell it how many cut points we want in there. And we'll just say 40. So this will return an array with 40 evenly spaced numbers between 0 and 200. And then these will basically be used as the cut points and determine where our bins are placed. So we'll use the same bins for both histograms. Just makes it easier to see the differences. The next parameter we'll pass in is the alpha parameter. And this just tells it how dark we want the shading of this histogram to be. We'll use 0.5. Then we pass in normed equal true, and this will normalize our plots to the same scale. So this is helpful because there's a lot more ham, for instance, in this data set than spam. So if we don't normalize, it'll just be the count. So the ham histogram will dwarf the spam histogram, and it'll be really difficult to tell the differences here. So this normed one just puts them on the same scale. Then lastly, we'll tell it what we want the label to be. We want the label to be spam for this one. And that'll be for our legend that we'll add in just a second. So let's go ahead and copy this line down to the second line, and we can just change the pieces that we need to change. So we'll change spam to ham, and then we'll just change the label to ham. And now that we've passed in labels, we can create a legend. We create the legend by doing pyplot.legend, and then all we have to do is tell it where we want it on our plot. So I'll say, let's put it into the upper left. And then we do pyplot.show. What that does is it takes this object that's been created and actually prints it out in our notebook. So let's run this import statement, and then we'll run our plot. Wow, so you can see that body length is very different for ham versus spam. So spam text messages seem to be quite a bit longer than regular text messages. So it appears that this extra feature could be really helpful for the model to distinguish ham from spam. So if we didn't create this feature, the model may not have necessarily picked up on this difference. Now let's evaluate our punctuation percentage feature. So we can just copy all of our code down here. We need to change the bins because the scale is different than it was for body length. So this is on a percentage scale. So let's make the upper bound 50. So that's saying, I'm guessing none of the text messages have greater than 50% punctuation. But we'll still leave it 40 bins. So again, this will create an array from 0 to 50 with 40 evenly spaced numbers. So now we need to change this from body length to punct percent. So this just tells us, again, we're doing the same filter so that it only selects the rows where the label is spam, and then it looks at the punctuation percentage column. Then we want to do the same thing right here for the column that is selecting the rows with label equal to ham. And then we'll just change the legend. We're going to put it in the upper right this time. And then we'll run that. And now you can see there's not nearly as much of a difference in punctuation used. You can see that spam might be a little bit more concentrated here on the left, whereas ham tends to have more of a tail over to the right-hand side. However, it's pretty clear which one of these new features is likely to help out the model the most. So, in terms of our original hypotheses, our hypothesis that spam messages tend to be longer than non-spam messages seems to be correct based on this evaluation, and this feature is likely to provide some value to the model. However, our hypothesis that ham messages contain less punctuation than spam doesn't appear to be accurate, and it isn't quite clear whether this feature will provide value to the model. Now, in cases like this, where there is some separation between the distributions, typically we'll err on the side of leaving this feature in the model just to see what kind of value the model itself may be able to extract out of it. So this is an example of how you might evaluate whether some newly created features will be useful to the model. Now that we've generated a couple of new features, we're going to take a look at whether either of them might be a fit for a transformation. Again, this is a pretty large area with deep theoretical underpinnings, and I'm only going to hit the tip of the iceberg here, so I encourage you to dive in more on your own. First, we'll read in the raw version of the text, just like we have in the last few chapters. And then we're going to create our two new features, and then we can print out the first 5 rows. So this looks just like it did at the end of our last lesson. So now, in order to determine whether a transformation might be helpful, we can look at the distribution of our data using a histogram. Now in the last lesson, we looked at the normalized overlaid histograms, but we didn't look at the full histogram, so we're still not exactly sure what the full distribution looks like for these new features. We only know when it's split by label. The first thing we'll do is look at those full distributions, and then we can determine which one might be a fit for a transformation. Now, what we're looking for here is a dramatic skew with a really long tail or maybe a few outliers. These are scenarios that would make a feature a prime candidate for a transformation. So, just like last time, we'll import pyplot, numpy, and then we'll declare matplotlib inline. And then we can go ahead and run this. And now for our histogram, we'll do body length first. So the first thing that we're going to do is create our bins just like we did in the last lesson using the numpy linspace function. We'll tell it to start at 0, go up to 200, and create 40 bins. So again, that'll create basically the cut points of where we want our bins to begin and end. Now we can call pyplot.hist, and we're going to pass in data in the body len column. And then we'll just tell it to use the bins array that we just created to create the bin cut points. Now for our data, if you remember last time, we filtered our data frame. This time we want the entire histogram, not just where the label was spam or ham. We want the entire thing. We want to see the full distribution. Using these bin cut points, we're not passing in alpha, normed, or label like we did last time because we're not comparing two different distributions. So let's go ahead and give this histogram a title, and we'll call it body length distribution. And then now that we've constructed this pyplot object, we'll go ahead and tell it to show it. This distribution makes sense We saw that spam were mostly long, and so those are the ones concentrated down here, and real texts are mostly short, so those are the ones kind of concentrated down here. So you see kind of this bimodal distribution here with two different spikes. I wouldn't say this is a great candidate for a transformation because it's not really heavily skewed and there's not really any clear outliers. Let's go ahead and copy this code, and then we can do the same thing for our punctuation percentage feature. We'll change the range of our bins. We don't want to go up to 200. We'll just go up to 50 now. And we still want 40 bins. And then we'll change the feature that we're running this on from body length to punct percent. And then we'll change the title from body length distribution to punctuation percent distribution. And then we can go ahead and run this. This one could very well be a nice distribution for a transformation. It's fairly skewed here where we see a lot close to 0, and then we see this tail out here extending all the way out to 40 with some of these outliers out here. A model might dig too much into the skewed tail over here and generate a model maybe that's a little bit biased. So we're going to focus on this feature for our transformations. In the next video, we'll take a look at Box-Cox power transformations as a tool to clean up this feature. So now that we've identified a feature to transform, it's time to tackle the elephant in the room. What is a transformation? A transformation is a process that alters each data point in a certain column in a systematic way that makes it cleaner for a model to use. For instance, that could mean squaring each value or maybe taking the square root of each value in a given column. So let's say a distribution for a certain feature has a long right tail, like this one does in this image. Then the transformation would aim to pull that tail in to make it a more compact distribution, like we see in the example here using a log transformation. We do this so that the model doesn't get distracted, trying to chase down outliers in that tail. The series of transformations that we'll be working with are called the Box-Cox power transformations. This is a very common type of transformation. The base form of this type of transformation is y to the x power, where y is the value in an individual cell, and then x is the exponent of the power transformation you're applying. You'll notice that this table shows some common power transformations using exponents from -2 up to +2. For the first line in the table, with an exponent of -2, that translates to y to the -2, which is the same as 1 over y squared. So let's introduce an example here. Let's say that 50% of the characters in a given text message are punctuation. So the value in that cell will be 50. So let's go through these different transformations and see how that would impact the transformed value. Starting with the first line, 1 over y squared. So in this example, that would be 1 over 50 squared, or 1 over 2,500. And that'll give you 0.0004. Then the next transformation is just 1 over 50, and then it's 1 over square root of 50, and so on. So this kind of gives you an idea of how different power transformations alter the original values. In practice, what this process looks like would be as follows. First, you determine what range of exponents you want to test out. So in our example, we had a range from -2 to +2, and that's a commonly used range. Then you would apply these transformations to each value in the feature that you'd like to transform. Then you would use some criteria to determine which of the transformations yielded the best distribution. You can read about what different criteria you can use to determine the best distribution, but today we're just going to plot it in a histogram and pick the one that looks the most like a normal distribution, because this means it'll be a nice and compact distribution that will be easier for the model to use. Let's go into our Jupyter notebook and pick up right where we left off in our last lesson. So you'll want to go ahead and run all the prior cells, and then we can get started with transforming the punctuation percentage feature. So what we want to do is apply a bunch of different power transformations and pick the histogram that looks the most like a normal distribution. So what we're going to do is we're going to set up a for loop to loop through some different transformations and just plot the data with that transformation applied. We'll do for I in some list of transformations, and then we can call our pyplot.hist function. And what we'll do is we'll say data, and we'll call the punct percent column from that data. And this should look familiar. This is pretty much exactly what we were doing before. And the only difference is that instead of taking that raw punct% feature, we're now going to apply some transformation. And I'll come back to what this exponent actually represents in just a second. And then we need to tell it how many bins we want. So this time we're just going to say 40 bins instead of defining what the actual cut points are, because our scale will change depending on what exponent we apply to it. We can just say pyplot title to add a title. And as we're looping through this, each time we want the title to represent what transformation we're applying. So we'll say transformation 1 divided by bracket, and then we'll tell it fill in that bracket with I. And I is going to be an integer, so we'll just tell it to convert it to a string. And then lastly, we'll do pyplot.show. So now, what are we filling in as our potential transformations? So I can already tell you that for our data, the negative exponents laid out up here is not going to work very well. So we're going to stick with positive exponents. So let's loop through 1 through 5. And so I will represent the denominator in our exponent. So what this is going to look like is for the first iteration through, it'll take 1, and so it'll be 1 over 1. So that'll actually just be the original punct% distribution. Then we'll take 2, so now this will be 1 over 2, and any number raised to the 1/2 exponent is just the square root of it. So the second loop through will apply a square root transformation. Then we're going to take 3, and it'll be 1 over 3, and so on for 4 and 5. So let's go ahead and actually run this. Now for the first loop through, you'll see that this is the exact distribution that we saw before. Now as we move to the next one, the square root transformation, or exponent of 1/2, you can see that it's kind of starting to pull this tail in. You can see how much the scale has changed, and you see it looks a little bit nicer, a little bit more compact, a little bit more like a normal distribution. Then you go to 1/3, and it's even more so, more compact, more like a normal distribution. 1/4 is a little bit better, and then 1/5 is even better. Again, you'll notice that the outliers continue to get pulled in closer and closer to the center of the distribution. So given this view, I would probably choose a transformation of either 1/4 or 1/5. Both of those look pretty good. Before we move on, I'll just note that you do have this stack to the left, and all these are just zeros. So this means that there's no punctuation. So any power transformation of 0 is just going to keep it at 0. So we'll maintain that stack on the left. What we're mostly concerned about is the rest of the distribution, seeing how the transformation affects that. So these power transformations are a commonly used method to transform skewed data or data that isn't behaving particularly well. It helps your model key in on the data and leverage it to make predictions in a cleaner way. Like I said before, there's a deep theoretical underpinning to this, so I really encourage you to dig into this a little bit more to understand why, when, and how you would transform your data. We've finally gotten here, where all of our hard work on crafting a dataset may finally pay off in building a quality machine learning model. But before we dive in, let's first try to define what machine learning actually is. Now, if you ask 10 people, you may get 10 different definitions of what machine learning is. As an illustration of that, here's a few widely accepted definitions. The first is one of the more well-known definitions. It comes from Arthur Samuel. Samuel originally coined the phrase machine learning in 1959. Yeah, it's been around that long. Samuel was a pioneer in computer gaming and artificial intelligence. He defined it as the field of study that gives computers the ability to learn without being explicitly programmed. So the next is from Tom Mitchell, who is a computer science professor at Carnegie Mellon. He defined it as follows. A computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. More or less just saying that machine learning is a set of programs that improve on a certain task with more experience or data. I think that gets a little closer to a reasonable definition, but still a little bit abstract. The next is from the University of Washington, without any name attributed to it. And I do like this one. Algorithms that can figure out how to perform important tasks by generalizing from examples. This is the first one that really gets at the core. Machine learning is training an algorithm on a set of known examples with the clear goal of generalizing to unseen examples. That's the entire purpose. The last example is from NVIDIA. They say machine learning is the practice of using algorithms to parse data, learn from it, and then make a determination or prediction about something in the world. I like this one as well because it gets to the piece of parsing data while maintaining what I liked from the previous example about learning from given data and use that to make a prediction on new data and generalize to say something about the world. So there are a few different viewpoints on how to formally define machine learning. The point being is that there is no clear, agreed upon definition, but hopefully given these 4 definitions, you'll start to develop an idea of what machine learning is. Now, there are 2 broad types of machine learning. The first, supervised learning. This is where you have an explicit label, and it's a task of inferring a function from that labeled training data to make a prediction on unseen data. So again, like we saw before, fitting a model for the purpose of generalizing and making a prediction on unseen data and saying something about the world. Supervised learning is the type of machine learning that we'll be doing in this class. Unsupervised learning is where you don't have any explicit labels, and it's about deriving structure from the data where you don't know the effect of any of the features. In other words, you don't have anything you're trying to predict necessarily. You're just trying to back out some sort of information or structure using the variables that you are given. A couple quick examples. An example of supervised learning would be a spam filter. The machine learning model would predict whether any given email is spam based on known information about the email. So email content, maybe sender, recipient, what time it was sent, maybe the structure of the email, things like that. An example of unsupervised learning would be grouping together similar emails into distinct folders based on the content. There is no right or wrong answer necessarily, but if a model can identify that these 15 emails are all in regards to a vacation to Italy, and those other ones are about planning a certain family gathering, and then it can group those together into their own little bundles. That's what unsupervised learning is. One more lesson of building up the tools and infrastructure we need before actually getting into the real machine learning. In this lesson, we're going to cover some of the tools to evaluate our models. There are a lot of different methods and metrics that you can use, but I'm going to stick to covering the ones that we'll be using just in this chapter. So the first thing that we need to define is a holdout test set. This is a sample of data that's set aside and not used in any of the fitting of the model for the purpose of evaluating the model's ability to generalize to unseen data. So this is meant to simulate how the model will perform in real-world scenarios. So this is the entire point of building these models, to generalize and say something about the world. Now, given that concept of a holdout test set, hold that in the back of your mind for just a minute. We'll be primarily using k-fold cross-validation to evaluate our models. In this process, the full data set is divided into k subsets, and the holdout method is repeated k times. That is, in each iteration, one of the k subsets is treated as the holdout test set, and the other k-1 subsets are put together to train the model. The purpose is that this gives you a little bit more robust read on the performance of the model rather than just having one single holdout test set for the model to be evaluated on. Now you have k test sets and k evaluation metrics to understand the potential performance outcomes. Let's walk through an example of what cross-validation actually looks like to make sure we're all on the same page. In this example, we'll start with a full data set of 10,000 examples, and we want to run 5-fold cross-validation. So again, that means k equals 5. So the first step is to split that 10,000 example data set into k, or 5, subsets. So you'll see that we now have 5 subsets of data, and each has 2,000 examples. So this is sampling without replacement. So all 10,000 examples are still accounted for. And it's worth noting that these subsets will remain the same throughout this entire process. So an example in subset 1 will remain in subset 1 all the way through the end of this cross-validation. We assign one of these subsets as a test set, which is subset 5 in red here, and then we assign the other 4 that are in blue to the training set. Now we'll fit a model on the 8,000 examples in blue, and then we'll evaluate the model on the 2,000 example test set in red. And then we'll record the performance metric and store that away in an array. To be clear, this is all handled under the hood in scikit-learn. You don't have to manually implement these steps. You'll see when we actually write this with code that scikit-learn handles all this, but it's important for you to understand what it's doing when it carries out this process. Again, you'll pick an evaluation metric, and after the first iteration, it'll store the performance of the model on the holdout test set. So here we're saying that's 0.867. Next, we'll move on to the second iteration, where now the fourth subset is the test set, and subsets 1 through 3, along with the fifth one, are now the training set. So again, we'll refit a brand new model on these 8,000 training examples and evaluate on the 2,000 test examples in that fourth subset. And then we'll store the performance metric. Here, we're just saying that's 0.884. Then again, for the third iteration, the third subset will be our test set, and then the model will be trained on the 8,000 examples in the first, second, fourth, and fifth. So you train a brand new model, evaluate it on the third subset, store the performance metric. Here we'll say it's 0.901. Again, for the fourth iteration, same process as before, but now the second subset is our holdout test set. Last but not least, the first subset is the test set, and 2 through 5 are the training data. Fit a model, evaluate it on the first subset, and store the evaluation metric. Now, it's worth noting that at this point, every subset and thus every example has been used in a training set 4 times and in an evaluation set once. So we have now used this model configuration to fit a model on all different combinations of these examples and evaluated it on every single point in this dataset. So you can see why this can be a really powerful tool to gauge a model's ability to generalize. And then lastly, you would normally output maybe the full array of scores, so all 5 scores, or you might just output the simple average. So the average is 0.885, but now we see a more robust gauge of what the potential outcome of this model would be. So let's just say we're using a single holdout test set and using that to gauge the performance of the model for our business. Now the first iteration yielded a score of 0.867, but an average over all 5 is 0.885, and the highest is 0.901. So that's a difference of 0.018 from the lowest score to the average and 0.34 from the lowest score to the highest score. That may not seem like a big difference, but in a business setting where this could impact millions of dollars, that's a huge difference. So having a read on how this model performs over 5 different test sets is a huge advantage to truly understanding how your model might perform in the real world. Now this gives us more confidence that the model will perform around 0.885 and gives us a range of plausible outcomes or some error bars on the projection. So let's talk about actual evaluation metrics now. So for a classification problem like this spam ham dataset that we're working with, we'll generally use 3 main performance metrics. The first is accuracy. So that's just the number that you've predicted correctly over the total number of observations. So if you have 10,000 observations and you got 800 of them labeled correctly, then your accuracy is 80%. The second metric is precision. Within the context of the problem that we're working with, that would be represented by the number that the model predicted as spam that are actually spam, divided by the total number that the model predicted as spam. And the last evaluation metric is called recall. So that would be the number predicted by the model to be spam that are actually spam. So again, that's the same numerator as precision, but now it's just divided by the total number that are actually spam instead of the total number that are predicted as spam. So that's accuracy, precision, and recall. So I like this visual representation of precision and recall. You can see that the numerator in both is the same, the amount that you correctly identified, but the denominator is different. Precision is all things that you said were relevant, while recall is all the things that are actually relevant. So in our example, relevant means it's spam. So now, precision and recall give you the ability to kind of tailor the aggressiveness of your algorithm based on your business problem. For instance, if false positives are really, really costly, then you'll want to optimize your model for precision. But if false negatives are really, really costly, then you'll want to optimize the model for recall. Only knowing accuracy may not really give you insight into this kind of trade-off, and we'll dive deeper into those specifics as we start to build our own models. So now that we understand some evaluation metrics that we'll be using, and we understand how to actually use those to evaluate the model, I think we're set to actually build some models. We're going to start getting into some actual machine learning now, starting with an introduction to random forest. Once I introduce random forest from a conceptual level, we'll jump into fitting and evaluating our own random forest model in the next lesson. I want to first note that random forest is one type of a machine learning algorithm that falls into a broader category of ensemble learners. This takes advantage of the ensemble method, which is a technique that creates multiple models and then combines them to produce better results than any of the single models individually. The idea behind ensemble learning is that you can combine a lot of weak models to create a single strong model. The basic idea is that this leverages the aggregate opinion of many over the isolated opinion of one. This method has a very strong theoretical motivation. With that said, we're not going to get into those details in this course, but it's just one of the many reasons that ensemble learning is a very popular method in machine learning. With that context, let's jump into defining random forest. Random forest is an ensemble learning method that constructs a collection of decision trees and then aggregates the predictions of each tree to determine the final prediction. So in this case, your weak models are the individual decision trees, and then those are combined into the strong model that is the aggregated random forest model. So you may say, I want to build a random forest model to predict ham or spam. Let's just say that the random forest has 100 decision trees in it. Then each of the 100 decision trees are built independently of one another, and each will output a prediction of either spam or ham. So let's say 60 of those decision trees vote spam and 40 vote ham. Then the final prediction of the random forest model will be spam. So it's really just a simple voting method for the trees. There are a lot of benefits to using random forest. It's a very versatile and powerful machine learning algorithm. For one, it can be used for classification or regression, so that means a categorical response or a continuous response. It easily handles outliers, missing values, skewed data,